We'll get started with our program shortly, but first, I want to go over some important details to help things go smoothly. So we can go to the next slide. Firstly, please keep your video off unless you're presenting. This will help us conserve bandwidth and reduce clutter on the screen. Next, please send your questions for our speakers in through the chat function. Most of you can probably find it at the bottom right side of your screen or in the center at the bottom. As a note, this workshop and chat will be recorded. Registrants have been pre-assigned to their breakout rooms. We recommend using the computer audio or call me function when you sign in, as this will help you avoid issues when we split you into the breakout rooms. And finally, if you're having audio issues, which we have noticed some people having, if you log in, if you check your audio before connecting to audio, this tends to resolve the issue. And with that, just wait for the screens to come back up. I'd like to introduce Sven Mume. If we go to the next slide. Sven is a technology manager in the Buildings Technologies Office at the U.S. Department of Energy. He is the emerging technologies lead on opaque building envelope and thermal energy storage materials research and development. He also contributes to BTO's technology to market initiatives. He will now go over the workshop objectives and goals.
Great. Thanks, Nelson. Again, welcome to the Thermal Energy Storage Systems workshop. It'll be a great two-day event. We have over 750, 760 registered attendees, so it'll be great. So here are the highest level objectives for our two-day workshop, which includes identifying technology gaps and research needs to overcome market adoption barriers for thermal storage in buildings. We'll discuss the state of technology. We'll discuss that state-of-the-art technology development, as well as the pathways to widespread thermal energy storage deployment. And your feedback is going to be really, really important to inform our BTO's thermal energy storage research and development, demonstration and deployment roadmap, as well as future pre-competitive R&D funding opportunities in this space. And lastly, really importantly, we're seeking to build a community among thermal energy storage stakeholders. We have an ambitious goal to decarbonize the building sector, to decarbonize the overall economy. And we think that thermal energy storage will play an integral role. And we really want to build this community to drive towards this common goal, and we can do great things together. Next slide, please. So here's the agenda for day one on opportunities, value drivers, and barriers for thermal storage. We'll have some great keynotes, including from David Nemzo, our Director of the Buildings Technology Office, Margaret McCracken from CalMac. We'll also have some really lively, pretty packed panel discussions to really get the juices flowing for the breakout sessions. And this is where we really want to have all of you provide your feedback, your input, and please engage. We really want to hear from you. And with that, next slide. And Nelson, back to you.
Yeah, thanks. So we will now have some opening remarks from Dr. Peter Green. Peter Green serves as Deputy Laboratory Director for Science and Technology and Chief Research Officer for National Renewable Energy Lab. He's also Senior Vice President of the Alliance for Sustainable Energy. In his role as Deputy Laboratory Director for Science and Technology, Peter is responsible for NREL's science and research goals, strengthening the lab's core capabilities, and enhancing NREL's research portfolio. And now, Peter Green.
Thank you, Nelson. Let me bring my presentation up. And yes, let me begin by welcoming you to this workshop. I'm delighted to be a part of it. I think we're all quite committed to the goals of this new administration for good reason, namely to achieve a carbon-free power system by 2035 and 100% clean energy economy by 2050. Over the years, DOE, with some really key investments, has laid a foundation for us to be able to potentially achieve this in time. And a big part of this really is this transition from the grid of Edison, which is essentially sort of fossil fuel based, where power is generated centrally. There's one-way power flow to customers and very limited communication. Ultimately, the goal is to get to a carbon-free energy system where we're going to autonomously control millions and millions of devices and distributed energy systems by and large. This new grid system, the future grid system, is going to be reliable, resilient, and secure. And certainly, trying to avoid cyber-type messes like what happened this past weekend. It's going to be a fundamental different grid. One that's going to be inverter-based largely because we're going to be incorporating renewables at really, really high levels. And if we have variable renewables, wind and solar, then storage becomes a key part of that. And in fact, as far as storage is concerned, thermal storage has a lot of potential. Largely, it's going to reduce the carbon footprint.
Dr. Green?
Yes.
Can you show your slides full screen, please?
Oh, thank you.
Yep. Thanks.
Yeah.
Thanks, Dr. Green.
Yes. So, so thermal storage, as I mentioned, is going to be a key part of this because of the lower costs and efficiencies, peak shaving, and certainly contributing towards the sort of the balancing the supply and demand. And so that's where it's going to fit in. And so what I'd like to do is spend the next few moments just telling you a little bit about NREL and explain to you how we fit into this overall strategy and what our contributions are going to be. And certainly, many of you who have worked with us realize we have a great number of partnerships. We began as a lab in 1977, and it's noteworthy that this came at the end of the energy crisis of the 70s. And it really was a result of that. And it was a time during the Carter administration. And today we have about 2,900 people. That includes over 300 postdoctoral researchers, grad students, and undergrads as well. So postdocs play a key role in the work that we do. We have over 900 partners, and this ranges from large companies from, on one end, you have GE and Exxon, GM, Eaton. To another end, we have cities like LA, to other small towns around the globe that we've helped make a transition towards a sort of a clean energy type environment. So this goal, what the vision of NREL in the end has always been for a clean energy power system and economy. So back in 1977, we weren't called NREL, we were called the Solar Energy Research Institute, SERIA. Some of you may know this. And work began in the era of solar. And I mentioned this because at the time, the work not only included very basic science, but also had to demonstrate level of viability. So the lab researchers worked with industry as a way to get things to market over time. And so the DNA really is from the fundamental science towards innovation, validation towards markets. And this is an example. The world's most efficient solar cells is multi-junction solar cells, which are too expensive, so they use in space or military applications. That's an NREL technology as an example. Wind became another key aspect of our work. The modern day wind blades, again, was certainly developed by NREL with a range of industrial partners. So the partnership is very key to what we do. There's a lot of work on water and there's geothermal energy. Geothermal Vision, Geo 2020, is really a goal to make geothermal available across the entire nation through advances in technology. Sustainable transportation is another area, so bioenergy, biofuels, either from biomass or from carbon capture and conversion, potentially for aviation and certainly marine applications largely. There's hydrogen economy. There, we're thinking of the coupling of hydrogen with a new future grid system for storage. Energy efficiency, we're going to hear a lot about that to the buildings. I won't say very much because we're going to hear a lot more. There is a key part of NREL strategy going back to the early 1980s, by the way. And of course, there's the energy systems integration. Many of you are familiar with EASE, a sort of a unique facility around the globe for looking at advanced energy technologies. We'll work with utilities and cities by and large. Security and resilience are a key part of how we think about energy systems integration. That's absolutely necessary. If we can't address the security and resilience issues, it will undo a lot of the work that we're trying to accomplish. So I'd like to now give you a sense of how we think about the future. And I find it fascinating that since the energy crisis of the 70s, and I remember this because I was a teenager, a college freshman back at that time when the lab started, the global population has doubled. And what we find is by 2050, we're going to increase in population by about 20%. And our energy use is going to go up by 40%. And certainly we're on track to simply accelerate the rate at which we're sending CO2 into the environment. And and this is largely because the emerging economies are growing really quickly. They're growing much more rapid than us in the West, for that matter, and they're going to be trying to be using energy any way that they can. But on the good news, though, the wind and solar have dropped in price significantly. Another case in point, since 1977, the cost of solar has dropped by 2 orders of magnitude. So they've now become sort of viable. But what also has happened in the meantime is that there's now distributed energy generation across the entire country. It's no longer centrally there. And we're looking at EV adoption. All the indications now in the last few months is that EVs are going to be a key part of the economy in a short period of time. So what I'm showing you right now is we look at these trends by and large, and we did some really careful planning. NREL together with DOE colleagues, together with partners. In fact, many of you on this workshop likely participated in discussions with us in terms of how do we identify new directions and pathways that will ensure the long-term viability of NREL. And so there are 3 key areas we investigated. One is the largest effort is in integrated energy pathways, and this is an area where NREL has always had an area of strength. For now, let's think of it as enabling the grid of the future, and I'll say some more about this. The other one is electrons and molecules. The idea ultimately is taking things like cheap substances like CO2 and water and converting them to more valuable products. And then the third area is the circular economy. We can't continue throwing things in a landfill. In the next decade or so, we're going to have to increase the amount of wind power generation and solar by about an order of magnitude each, which means that we're going to have to be building facilities, building infrastructure, and we can't keep throwing things away. So we're going to have to find a way to minimize waste, which means that potential new materials, new processes, new designs for that matter. So let me say a few words about the integrated energy pathways. So as I mentioned to you earlier, we're now in this new era where there is power generation from lots of locations, rooftop solar, there's wind farms. We're looking, for example, at wind farms in offshore wind. That's another big part of this. And so these are no key things. There's this new direction, green interactive buildings. We're going to hear a lot about that soon, so I won't say anything more beyond this. We're looking at mobility, autonomy, controlling fleets of cars. This is another area that we're thinking really carefully about and working again with partners. Advanced wind plants, again, trying to optimize the production of wind facilities. Lots more to be done. Won't say any more. And then, of course, the advanced solar plants and advanced solar technologies. And so this is how we're thinking about the future. There's a lot of work done at NREL in sort of trying to design, at least from a computational at this stage, what these new systems look like. There's a lot of work done right now from our own investments on trying to look at an autonomous energy systems for cities, and in some places it's actually being tried out and executed in some ways. And that's another conversation for you by and large. But ultimately what we're looking at then is right now controlling millions and millions of devices real time. So you take a city like San Francisco and you think of the typical homeowner may have an EV, they have a smart They may have a smart thermostat. They may have electric heating. So these devices for a typical city may be millions and millions of maybe millions of them in a given city. And so as we think about how do you implement something like this, and there's a new program which we at NREL we call ARES, and it's Advanced Research for Integrated Energy Systems. And think for a moment, we've got the ESIF facility, which has been around for many years. Many are familiar with it. And then, of course, there is our Flatirons campus with wind, megawatt capacity wind, megawatt capacity solar, megawatt capacity batteries, and all kinds of energy assets out there. And together with our high-performance computing facilities, we can actually begin to think really carefully about what do we need to do to design this or to accomplish this. And so ARES really is a research platform that takes advantage of ESIF assets, the assets of the Flatirons, the wind and solar storage, together with the emulation capabilities enabled by high-performance computing, that we can actually think about how do you develop solutions to design and construct a future autonomous energy system subject to all the constraints that we have to meet. And indeed, power electronics is key because so we make in context to all of the renewables nowadays. It's no longer synchronous as we did for the fossil. And energy storage is a central part of the 5 areas of research that we're looking at. Quickly, electrification is going to be key. The most significant sort of opportunities exist with transportation and industry. I won't say much about because you hear more about this. Just as a case in point, an EV, if it's charged by simply power coming from renewables, is about over 3 times more efficient than internal combustion engines. So as soon as the battery costs drop for the vehicles, they're going to hit cost parity with the internal combustion engine vehicles. And since they're going to be cheaper to maintain, it could be a draw for most people. So the other area is circular economy, and I alluded to the fact that I just pick one example, right? You take wind blades. Tens of millions of metric tons of them are going to be thrown in the waste. The future now is actually making wind blades, instead of making from thermosetting polymers historically, they're now going to be thermoplastic-based polymers, which means that they're much more easily recyclable. So that's one example of a design and manufacturing of a process or of a technology that ultimately you won't be throwing things in the waste. And of course, there's a whole range of other areas from the next generation solar like perovskites, facial solar we're thinking about, the plastics upcycling. I won't say anymore, but the idea is that you want to design and manufacture things in such a way that you minimize waste completely when it's done. You're not throwing something away and you can recycle. And we're also looking at very new material systems that are abundant in the US, enable us to manufacture anything that we need. So that's another one of the goals that we have. The third area now that I wanted to share about as part of our strategic direction is we call it electrons and molecules. Many of you know it as power to X. And really what we're doing is we're taking something like CO2 or hydrogen and finding cheap ways to convert this. The renewable power is essentially really, really cheap electrons that provide the power. Then, of course, there are really biotic or abiotic processes which enable us now to make new chemicals or new fuels, or in fact, new materials. And so all this can be done without the use of petroleum. And the CO2 is going to be captured from industry or captured from the air. A lot of work being done by researchers all over the world. So this is at the beginning, but the future looks really exciting. My last slide really is getting back to this topic, the thermal energy storage. I sort of feel compelled then, you guys know this well, the point then is that if you look at storage, it becomes a central part of the grid operation these days. The graph to the right is showing duration versus capacity. And if you look in terms of thermal storage, the potential is huge in terms of the capacity, in terms of the duration, going from hours to actually seasonal, which is going to be a key challenge. You know, I like to think of the thermal energy storage, thermal energy as kind of the last frontier in the sense that it's the most difficult challenge because one is the conversion. This is so much of it's just wasted. If you're going from fossil fuels to electricity, over 60% of it is lost as heat. If we think about storage, again, we're facing challenges with that. And in terms of the building applications, you learn this soon, right? I mean, the phase change materials, it's kind of interesting. When you teach college freshmen or sophomores material science and engineering, you tell them, look at intrinsic properties, those will guide you. And if you look at thermal store and the phase change materials, it's not just the intrinsic properties. That's only a very, very tiny part of it. It's really the environment and the amount of heat that's and the rate at which it's discharged. All of these things become really key things. There's a recent Nature Energy paper from the NREL guys pointing that out. And finally, there's transport. Transport to do with losses there. But all of these ultimately are materials challenges by and large. The physics we can get around if we're clever about the materials challenges. We've seen this time and time again, but this thermal issue is a vexing one. I think that's why we're all here today. And so I want to wish you guys good luck. It's a challenging problem, but there's no really room for failure. So with this, let me turn this back over to the moderator.
Perfect. Thanks a lot for that, Peter. So next, we will hear from David Nemzo. David Nemzo is the Building Technologies Office Director within the Office of Energy Efficiency and Renewable Energy. David brings to EERE more than 3 decades of experience in the industry, including running a large state government and energy and water department, a prominent bipartisan nonprofit Energy Efficiency Association, and an energy consulting practice. Welcome, David. The floor is yours.
Thanks very much, Nelson. I really appreciate that. I'm not sure I like your tone when you say more than 3 decades, but I suppose I can live with that. So it's great to see everybody, and we're very delighted at the Building Technologies Office in DOE to not only host this session, these 2 days, but to have your time, attention, and intellectual and moral support. I'm going to put up some slides in a moment, talk about buildings and storage briefly, but before, I should say, as I do that, let me get sharing here. I will. As I get. That's shared, correct, Nelson or Sven?
Yes, we can see your slides.
Okay, great. So look, I want to at first acknowledge Peter Green. Thanks, Peter. What you said today was very interesting, and those big issues that you raised help set the stage for our 2 days of work on thermal energy storage. And I do want to give a special shout out to my immediate colleague Sven Mumi at BTO, who is our commander in chief on these issues, and as well as to Nelson James and to Lynn Trong and the entire team at Oak Ridge, Berkeley Lab, and NREL, who helped us organize this session and work with us on this issue. And of our many distinguished speakers, I'll give one shout out, and that's to Alejandro Moreno, my close colleague at ERE, who's our new Deputy Assistant Secretary for Renewable Energy. So this is 2 days when we want to cover these issues. You heard from Sven, you'll hear from me too. I just want to underscore what Sven said are our goals over the next couple of days, but I will save that for the end. First, I want to let you know what we do for a living at DOE and the Building Technologies Office, especially in the last few months, as our mission has been made very clear to all of us at DOE, whether we're civil servants like Sven and myself, or lab staff or political appointees, and that is this: we are all collectively working to put the U.S. on a pathway, and an irreversible one at that, so that we can have a carbon-free power grid by 2035 and a carbon neutral clean energy economy by 2050. So those are rather ambitious goals, and as Peter just said, a failing isn't an option. I'll also quote Winston Churchill, who once said, in reference to an equally great challenge, sometimes doing our best isn't good enough. Sometimes we must do what is necessary. So pick your quote. So our goal at BTO and throughout ERE is to, well, especially at BTO and our sister offices, is to decarbonize the building sector. and with the trajectory by 2035, and we can't have a clean energy economy by 2050 unless we're simultaneously decarbonizing the building sector. It's that simple. And then you can see some of the other goals we have at the same time. We don't have the luxury of focusing on one goal, one daunting goal, but one goal at the same time. We're going to make progress on improving the affordability of buildings, their performance, their resilience. We need quality workers. We need both quantity and quality of a trained workforce, no matter what the clean energy issue is, whether it's familiar technologies or emerging ones. We want to make advancements in that workforce, not just on their quality, but also on their diversity of the workforce. We need help from everybody in this country, and thinking about equity and inclusion, particularly in STEM, but also throughout the clean energy workforce, not just the STEM subset. We want to ensure, we've been directed to ensure that a large share of the benefits of all investments, but certainly what we're responsible for, the federal part, are delivered to disadvantaged and currently disenfranchised communities, and not just to the enfranchised, more affluent ones, and much more. So it's that simple. Here's slide 2. Now, if slide 2 isn't challenging enough for you, if you don't think it keeps us up tossing and turning at 3 a.m. at BTO, then the next couple of slides certainly will. Real quick, just a bit of a pitch. Buildings are the largest sector of the U.S. energy economy, full stop. Buildings are a bigger part of energy use than industry or transportation. Responsible buildings together, and you can see this is residential in dark blue, commercial in whatever that is, battleship blue. Energy use buildings represent 39% of U.S. consumption. Electricity, it's just about 3/4, 74% of all electricity use in this country is in buildings. At peak, it varies certainly by region, but we're talking in most of the country about 80% of peak energy use comes from the building sector. Excuse me. And so you can see where I'm going next. CO2 emissions, 35%, over a third of carbon dioxide emissions in the US are buildings based. And that leads to a very large bill. US buildings, the 129 million commercial and residential buildings spend last year about $412 billion just on gas and electricity, let alone propane and fuel oil and other fuels. And so the stakes here are enormous. And that's why we're going to talk about that. Oh, here's the bad news. Pick your number. Some of you are going to give me grief saying 30% is too small, but it's at least 30% of energy use in buildings is wasted. So pick your metric there. That's at least $100 billion out the door every year that serves no productive purpose. All right, if that doesn't keep you up at 3 a.m., this one does. The diversity of the U.S. building stock, those, again, 129 million buildings, residences, and commercial buildings alike. I'm just here, you all know this, but just a friendly reminder. And as I hope you can see, everything I'm touching on today has a direct relevance to thermal energy storage in buildings, including that there are different building types used for different purposes in very different climates, where the U.S. is the size of a subcontinent, and so our needs, especially our thermal ones, vary enormously. And of course, nearly a third of residences are tenant occupied in the U.S., and close to just over 40% of commercial square footage is tenant occupied. So it leads to all sorts of issues. And at BTO, we work on all issues we can get our hands on when it comes to building performance. And we're going to talk about thermal energy storage, of course, over the next couple of days, but it's part of it's part of many bigger issues, not just energy storage, but it's part of the bigger issues of how do we make buildings and other loads, including manufacturing and even agriculture, how do we make buildings more demand flexible? How do we get more adept at taking those technologies and getting the same or better services, productivity and comfort out of them, but being more flexible with demand so we can shift across time of day, maybe even time of year, et cetera. And that's a lot of what we do. And again, the diversity of different communities in America, even if two buildings are the same, they could be in very different situations. I think it's pretty obvious to me, I hope to all of you, that to decarbonize the grid, and you heard from Peter and myself, as you know, the president has set a goal for the US that the power grid should be decarbonized by 2035. And to meet that ambitious goal, we'll have to have a enormous increase in renewables, not just renewables, but in variable renewables. Geothermal and hydropower, of course, are dispatchable renewables. They're not going to see the same level of growth by anybody's scenario that wind and solar will. And those variable renewables, wind and solar, whether distributed or central station, come with great attributes, being carbon free, being fuel free, but dispatchability is not among their great attributes. And so a lot of the action to make them more valuable and more available when best needed requires energy storage. And that storage can pick your favorite storage technology. And if it isn't thermal, well, harumph. But whether it's compressed air or battery, well, lithium-ion batteries or flow batteries or pumped hydro, whatever it may be, we're going to need more energy storage to help accompany the renewables revolution that this country is facing. And that demand flexibility will also contribute. Demand flexibility isn't storage, but it acts a lot like storage. And so this will only go up with decarbonization. Oh, by the way, part of decarbonization in most scenarios is to have beneficial or strategic electrification of end uses. And in buildings, that often means having electric heat pumps instead of fossil fuel furnaces, et cetera. So all the more reason to have more storage, including thermal. Look, I want to say something personal before I talk about this and turn over the floor. I used to be in the thermal storage business, as several of you know, Messrs. McCracken and Tropsa and Narayana Murthy, who I worked with. I was at ICE Energy, so I say that by way of revealing all my cards. I'm a big personal believer in the role that thermal energy storage can play, whether it's ICE or other approaches, including on the heating side, but especially on the air conditioning side. And I also was involved when the ESA still stood for the Electricity Storage Association. And many of us in the storage community, many of whom are on this meeting today, had a fight with the ESA and say, why are you the Electricity Storage Association? Why aren't you the Energy Storage Association? And we spent a lot of our time saying, me too, thermal too. And that's a cultural dynamic. I don't think that's a scientific dynamic. And I also helped create the California Energy Storage Alliance. So I just want you to know my prejudices and my background. I'm also an energy efficiency person. I can do both of those simultaneously. Thermal energy storage in most situations, not everyone, but in most situations, is by far the most energy efficient form of storage. All forms of storage have a round trip inefficiencies. As the joke goes, despite all our progress, the laws of thermodynamics remain unamended. But thermal storage has some of the lowest losses because of fewer conversions, especially when used for thermal purposes. And in many cases, such as for cooling, we can, of course, run the cooling equipment, the chillers or the RTUs at night using cool air, and then avoid having to cool mid-afternoon hot air. So we can get enormously high efficiency. So another one of thermal storage's great attributes is that if done in the right way, and if not stored for too long a period of time or try to shift over too long a distance, it can be by far the most energy efficient. Okay, back to the graphs, please. So if you look at this, you probably had a chance to read this while I was talking, and I hope it's quite obvious. We all know that weather and therefore thermal loads of buildings, over, depends where you are in the country and what building type, but a little over half of building energy use is thermally driven, heating, cooling, and water heating. And depending where you are in the country, that's most likely, in nearly all cases, going to drive peak. Look, we all may watch TV at different times of day, or we all may run our dishwashers at different time of day. I'll tell you what, we're all running our air conditioners, at least within the region, we're running our air conditioners at the same time of day as each other, and similarly on the heating side. So naturally, that leads to a maldistribution of air conditioning and heating use, and therefore contributes to system peak. So we know that. So if we can manage thermal loads better, we can manage the overall peak demand. So if you look here, we did some NREL and LBNL on the left, did some analysis for this workshop. And if you look on the left, they picked the ERCOT territory in Texas. I should ask them. I don't know if they picked it because ERCOT obviously was in the news a few months ago for the deadly crisis they faced. But they picked ERCOT, a growing area, and they looked at 2050. They modeled it out using DOE's Scout modeling tool. And you can see there that they looked at thermal loads in red, non-thermal loads. That's in that yellow, the ecru bone color, whatever that is on the bottom. And they also modeled out the renewable energy supply. And of course, it's on a 0 to 24 typical summer day in Texas. And so you can see the point we're making, that even though, as I said earlier, peak demand is in those air conditioning hours, in this scenario with PV and wind, peak renewable generation may also be at related times, but you see those shoulders there that are thermal load. So if we can use storage, if we can shift that part, so take the part of this graph that's in that red color, the two shoulders, minus the yellow color on the left shoulder, because that's non-thermal load, and within the green ovals, that's the part in this schema we're shifting. Within the green, that's red and no other color. If we can shift those shoulders, we can clip peaks and we can de facto shift renewables. And when you look at the numbers on the right there from this analysis, so for ERCOT, that's a shift of, that can readily be a shift of close to 200 gigawatt hours, 30 gigawatts nationally. The numbers are very significant. As you can see, 2,500 gigawatt hours that can be shifted, and 342 gigawatts that can be shifted by 2050 using the assumptions that the lab team led. And again, they're assuming they just picked a mix of half solar and half wind. Looking at the bottom there, and yes, I'm a thermal. I love all storage. I love thermal a lot, so a little competitive. So if you look at those two shifts, the U.S. number, U.S. pair of numbers there, that's the equivalent to 51 million Tesla Model 3 batteries. That's a lot of storage, and it can be done very cost effectively, very efficiently through thermal. I think we've covered this. This is just to say that not only is thermal available, not only can it do the job, but the value statement is very significant. Not all kilowatt hours were created equally. Not all kilowatt hours cost the same to generate. Therefore, the most expensive ones that it costs to generate, for example, if they're on peak and we're using the highest heat rate, oldest, least functioning members of the power plant fleet, because that's what you do, you save them for peak, in addition to the congestion on the T&D system, the R losses. It's the most expensive to generate in most situations a kilowatt hour at peak, such as a summer peak. Therefore, it's most valuable to save it. So if you look at that graph on the right, this is analysis done for us on by LBNL a few years ago. Take exit signs, you see that on the left, they run flat out, of course, 24/7. This is just one case. This is Massachusetts, and these are megawatt hours. Each one of these 5 single megawatt hour saved. Under this scenario, saving 1 megawatt hour worth of exit signage saves the system about $170. Saving 1 megawatt hour of residential AC saves the system over twice as much. You can see it, $370, because in addition to avoiding the fuel, you're saving even the base fuel, you're saving even more fuel, even more ambient emissions, more CO2 emissions, as well as T&D congestion. So again, at peak, it costs much more to produce, and therefore it's much more valuable to save. I hope you can all follow from home why that makes storage and thermal energy storage even more valuable. Real quick, I want to look towards the future. Look, you know, thermal storage has been around for a long time. The Romans harvested ice from the Apennine Mountains, and Thomas Jefferson had thermal storage in Virginia. But what's old is new again, and we have new technologies, and many of you do this for a living, use existing technologies and are constantly refining them. And at DOE, we want to support that. We also want to help develop new thermal storage options. So this is an example using ice storage, and by ice I mean a frozen liquid, whether it's H2O or some other, or a glycol mix or whatever it may be. It's using the phase change, and of course with H2O, that phase change is where the action's at. And water works great. Water is non-toxic, it's cheap as can be, it's readily available, but it's heavy. And so we also are looking at other materials that have different, that might be more dense, thermally dense, and have that's helpful in storage with the phase change, or might have different phase change temperatures that have different performance for different situations. So that's one way to do it. We talk about hybrid systems here. Again, you can have thermal storage that's a bolt-on to a heating system, or to, such as tiles, such as the Steffes company uses, or that could be a bolt-on to an RTU, such as Ice Energy uses, or that is added to a chiller system, such as CalMax system. Or you can also design it differently from the ground floor, especially using different materials, especially when there are significant weight or volumetric constraints that you want to look at new materials. But there's a range of choices within thermal storage, and we'll talk about that. And I want to say we want to look forward, and I don't mean to imply that there aren't enormous choices today, and I don't think technology is the greatest barrier to the widespread deployment and adoption of thermal storage. There are many other barriers, from inappropriate price signals to lack of knowledge and awareness, to insufficient attention to climate and renewable energy. But there's still a role for future technologies. This is one of the more exciting ones, and we hope within SVED, when we have the 10th annual BTO Thermal Energy Storage Workshop, I hope we'll be talking about tunable storage materials that are embedded in building envelopes and can be built right into the building. And by being tunable with a demand switch, that's an electric demand switch, or perhaps some other technology, can be used year-round for different seasons. In fall and spring, we don't need them to be insulative, and in other seasons, summer and also winter, we want them to be storage, so we can turn them on and off and tune them. So we're looking at the next generation of materials, whether it's tunable, or I can't say static, or non-controllable. We hope there'll be a next generation of materials, of products, but also, of course, of approaches, of, as I said, information and valuation and price signals, and knowledge and commitment from building owners and operators. We look forward to working with you. And I think you know how to reach all of us, but if not, just write down the part at the bottom. We all use the same email convention, and we're here to work with you. So again, thank you in advance for the 2 days we'll spend together on thermal storage, and look forward to working you on BTO on this whole breadth of issues from thermal energy storage to other forms of storage and demand flexibility to decarbonizing our nation's building stock. Thank you. I think I turn it back to you, Nelson. Is that right?
Yes, perfect. Thanks a lot for that, David. So we will forgo the questions for this presentation just to try to get back on schedule. Though, please do remember to put your questions in the chat and Q&A. I've seen some other comments about will the slides be made available. We'll work to see what we'll be able to post afterwards after the workshop. Now we'll move on to our first panel discussion. I'd like to introduce, this panel will be moderated by Dr. Ravi Prasher. Ravi is the Associate Lab Director of the Energy Technologies Area and Interim Division Director of Cyclotron Road at Lawrence Berkeley National Lab. He is also an adjunct professor in the Department of Mechanical Engineering at the University of California, Berkeley. Among his many accomplishments, he previously served as a program director at RPE, where he created building energy efficiency and thermal energy storage programs. Welcome, Ravi. The floor is yours.
Okay, can you hear me, Nelson?
Yes, we hear you.
I'm unable to share. I don't have the share option open to me. So how do I share the slide? One sec. Yeah, I don't have, it's enabled on my
I just turned it off. Yeah, I just turned it off, Ravi, but oh yeah, it's not, it's grayed out for me too now, suddenly.
You were just made the presenter, so you should see.
I should see now.
Ravi.
Oh, okay. You have a problem because I'm logged in from two computers. Can you let me do one thing? Hold on. That's the
all right. We can solve thermal energy storage, but we can't solve remote meetings. That's welcome to 2021, right?
Yeah. Actually.
Don't worry, Ravi.
Yeah. So I somehow or other, is there a way I can just send it to you and then you project it? I don't want to delay this meeting.
Do not send it to me because the DOE firewall is too slow.
I have, unfortunately, I'm logged in from two computers.
Nelson,
you can send it to, yeah, you can send it to me.
Nelson or Lynn.
Yep. Ravi, if you want to go ahead and send it to me, I'm happy to present it for you.
Is there any way I can just send it through chat by any chance, which may be faster? Okay, now I can share it. Hold on a second. I see a button open. Okay, thanks. That's good.
Ravi, excellent job building up the suspense. Well played.
All right. Okay, thank you.
It's worth the wait. And Ravi, if you want to show it in full screen.
Yeah.
Yep.
Sorry.
Great. Thank
you. Very good. Thank you.
Looks great. Thank you.
Thank you very much. So I'm very delighted to host this panel, the first panel, particularly after hearing David's very motivating talk about thermal storage and why it's needed. I'm Ravi Prasher. I am the Associate Lab Director, one of the Associate Lab Directors at Lawrence Berkeley National Lab. Okay, I don't have to belabor much on this slide. David already showed it to you. What is really exciting, particularly for this community who are we're all interested in thermal energy storage, is that that doesn't matter where you put the storage, whether you put it on the grid side or you put it distributed, you put it centralized, whatever architecture you choose. What this analysis shows you is that amount of storage that is needed just to provide heating and cooling, that the thermal load in buildings is going to be huge. And the number that David showed you is 2,500 gigawatt hours for short duration storage. And then what the analysis this team has also done is that if you also include long duration storage, because there are times when you don't have wind or solar available, that number is staggering, more than 100 terawatt hours. So the bottom line, the key message is that there are a lot of storage, doesn't matter where we put it and how we use it and what form, whether it's electrochemical or pumped hydro or whatever have you, or thermal, a lot of that storage will just go and provide heating and cooling. And that provides us an opportunity to come up with alternatives, or I would say complementary technology. That's one point I wanted to reiterate again. Another thing that is really important, as we know, lithium-ion battery has really revolutionized the world of storage. But the question is that how sustainable the material supply is going to be. And you maybe, if you are following the popular press, there was an article in New York Times 2 days back on some of the mining practices related to lithium extraction. So there's going to be a lot of pressure in figuring out sustainable way of lithium supply, and other materials goes in lithium and battery. There's a very nice article recently came out which looked at what are the things which will be needed in the future to provide lithium supply only for transportation. And on top of that, if we say that we are also going to use that for providing heating and cooling in buildings, there's going to be significant pressure on lithium supply. So again, we have to keep those bigger trends in mind while we are developing as a country our energy storage strategy. And that's what I would say thermal energy storage provides another approach to solving the same problem. But having said that, I think the call to action to this community, at least to me, is that how do we emulate or learn from the lithium ion community? I think they have done a fabulous job, in my opinion. I am a thermal scientist by background, but when I came to the lab, Berkeley lab 5 years ago, I came to manage an electrochemical battery group. And I learned a lot by listening and hanging out with the researchers who work in the field of lithium ion battery. So what I realized was that, there was a very nice nexus between national labs, industry and academia working together with DOE directly involved in it. I would like to highlight a few things. 1991, the three top automakers, Ford, GM, and Chrysler, established US Advanced Battery Consortium, and they worked hand in hand with DOE to develop a roadmap. And that roadmap really helped the research community in figuring out what are the right problems to solve, and which, if we solve, will make a big impact. So I think that is something which I think, at least I feel that it is something really needed in the thermal energy storage community. And then 1998, DOE EERE program on lithium and battery was established, and it has done wonders. A lot of advancement that we see in the lithium and battery today, and the technology came out because of the program from DOE EERE, Vehicles Technology Office program. Then Office of Science got interested. They started launching battery basic research programs. And finally, as you may know, in 2012, a large-scale energy storage hub was formed, which is in its 10th year now. It got renewed a couple of years back. And finally, this all research community, because of the way the research community worked, this culminated into the 2019 Nobel Prize in Chemistry. So I think a lithium ion revolution took place by national lab, industry, and academia working together towards a common goal. And I really hope in these 2 days, we brainstorm as a community that how do we develop a similar framework so that thermal energy storage, significant advancement can be made in a shorter duration of time. Then I'm very happy and I'm very glad that we have a very distinguished set of panelists participating in this panel. We have Alejandro Moreno, who is the Deputy Assistant Secretary for Renewable Power in EERE DOE. Then we'll get some international perspective from world-renowned expert in thermal energy storage, Professor Luisa Cabeza. She's a professor of thermal engineering at University of Lleida in Spain. Then we have Dr. Klaus Daniel. Actually, he used to be in Oak Lab working on lithium ion battery. Now he is recently joined as senior fellow and innovation team leader for sustainability, one of the largest thermal energy technology companies in the world. And finally, last but not least, Ram Narayana Murthy, who is a technical executive for decarbonization of buildings and communities at thermal energy storage previously.
Hey, Ravi, your audio is cutting out.
Is that better? Hello?
Yes, we can hear you now. Thank you.
But when did I cut off?
When you were just you were introducing your panelists, and you started with Ram.
Oh, I see. That's one. Okay. All right. So again, let me introduce Ram again. Ram has a very unique background. He now works in EPRI as decarbonization of buildings and communities. And in his previous life, he has also worked on developing thermal energy storage technology. So we will get to hear from him about his perspective. With that, let me welcome our first panelist, Alejandro Moreno, for a few comments, and then we'll follow in this order. And then we will have, I'll ask a few questions with the panelists, and then towards the end, we will open the discussion for the audience.
Thanks, Ravi. It looks like I do have the share button, so I'll go ahead and share my presentation as well. I assume somebody will tell me if they can't see it. Otherwise, I am Alejandro Moreno, as Ravi and David said. I'm the Deputy Assistant Secretary for Renewable Power.
Alejandro, can you display it so that under display settings, you're mirroring? We can see it in presentation mode.
I'm sorry, you can see it in presentation mode.
Yeah, you're sharing the wrong screen. You're sharing your viewing screen and not the one that we're supposed to be seeing.
If you can go up to display settings, you can switch that over.
I don't see anything that says display settings.
So when you're in presentation mode at the top.
Got it.
Perfect.
Better now?
Looks wonderful. Thank you so
Great.
much.
Sorry about that. Never seen that before. It's a day of technical difficulties. Glad to be part of the crew. Thanks for having me again. I'm Alejandro Moreno. I'm the Deputy Assistant Secretary for Renewable Power. And if David sort of gave the overview of the buildings side, I'm going to take a little bit to give an overview of storage writ large and sort of some perspectives and hopefully catalyze some thoughts from you all who really are the thermal storage experts on how thermal storage fits in. Clearly, energy storage, as David mentioned, is critical to DOE writ large right now, and in all forms. I'm going to put this same set of slides that David threatened to keep everybody up all night on, which is really looking at what DOE's goals are right now. And they're pretty ambitious, no kidding. I think everybody understands this and understands where this administration has come out and is asking DOE to focus on. But certainly from getting to both a carbon-free power sector, but even more broadly, a net zero and really carbon-free energy sector 15 years later is going to take all of the resources at our disposal. And storage is going to be absolutely critical in some areas, very obviously. And I'll go to the next slide for transportation, for example. I mean, it is the major way of decarbonizing the vehicle fleet, at least light duty vehicles, but certainly for buildings and certainly almost certainly for the power grid. I mean, there are different types of storage that have different applications there. But if you look at these priorities in front of us here, one of the many things that stands out to me is almost none of them can be done without storage, or flipping that around, one or more forms of energy storage would be incredibly valuable tools at either increasing the speed or reducing the cost of achieving these goals. The other thing I want to point out about these goals is that they don't align exactly to sector in the way DOE has traditionally organized ourselves. To program office, or even to my sector, which is focused on renewable power generation, or the energy efficiency sector where the buildings program sits. These are all pretty cross-cutting in nature. And that, I think, it reflects both needs that we're focused on. These goals here really align to those sectors that have the largest greenhouse gas emission contributions right now. But it really points to the value proposition of, sorry, I got a notification there. It points to the value proposition of really thinking about how technologies integrate with each other and how different technologies have a wide range of different use applications and different use cases. And so this is where what we call in DOE the Energy Storage Grand Challenge comes to play, and that is the effort that we've had over the last couple of years. It was officially launched in December of last year, but really developed at a staff level bottom up over the last few years that we call the Energy Storage Grand Challenge, which is focused on determining how the different parts of DOE can and should come together to accelerate the different types of storage research in the most sort of valuable way without duplicating the work that's done in individual offices, but leveraging that work and recognizing that while a lot of the technology office work is specific to individual technologies, the use case and the application for energy storage is likely to cut across many different offices and also involve the combination of many different technologies. And so, David, hopefully this gives you some confidence that your Me Too was heard. We certainly do not only include electricity storage in the Energy Storage Grand Challenge. That is a big part of it, bidirectional electrical storage, so electricity in, electricity out, but just as much look at chemical and thermal storage, and also really do look at flexible generation and flexible loads, recognizing that they provide a lot of the same services that storage does. The other two things I would point out is, of course, this involves many different offices. Most of the applied offices in DOE do some work on storage, including, I think, all 11 of the technology offices within EERE, where the buildings program and I sit. And also that it involves much closer integration across the different steps of the value chain, that we can't just do early stage research and sort of throw technologies over the wall and see who grabs them. But that we need to, starting from a lot of the early stage research and basic research that we do in the Office of Science, we really need to think carefully about where DOE can provide support, both in the technology development, but also in the evaluation, in the demonstration, in the development of codes and standards, in working with regulators, with utilities to incorporate storage into planning processes, into regulations, obviously, and understanding what data under what conditions is needed to attract private sector investment as well. And just as an example, you see here, just for thermal and chemical storage, some of the different programs that are engaged here. And this is going to be an acronym soup. The point isn't to understand each of those. It's just to recognize that every one of those different acronyms is a different office. The ones in bold are those within EERE that focuses on some element of thermal or chemical energy storage research, either you see in sort of the rows focused on a different type of R&D and application, and in the columns a different part of the value proposition or the supply chain. It's all over the place, and that makes sense because a lot of the research is different. But it doesn't make sense to not have it coordinated at all. And so what we again have been thinking through is what are the right ways to coordinate this, and one of the frameworks that we've identified is looking really at the application, so the end use case. And we've thought about storage now for the 6 different use cases you see here, and sort of families of use cases almost. The first is really focused on decarbonizing the power sector. The second on serving remote communities, both for electricity and other energy services, but those that don't have a lot of other options for energy. Third is on transportation and mobility. Fourth is really looking at network interdependencies, for example, buffering some of the interdependencies between the gas system and the water system and the power system. And the last 2 are focused on facilities and the services that they provide. One thing I would point out here is that with the exception of electrified mobility, I think all of these use cases involve buildings. They involve either storage that is particularly designed for buildings, or buildings will be the beneficiary of storage that's designed for the energy input into them. And so recognizing that a lot of the technologies that we will be talking about in this workshop, they're really critical throughout, and the way they integrate with other technologies and the value proposition that they provide is coordinated with that of other technologies is really critical to getting the best solution for any of these use cases. And the way we then align our work and are thinking about the framework to align our work within DOE is the last slide I'll leave you with. But again, really driving home that this isn't just about getting better widgets, but it's about understanding how they can be used and giving people the tools that they need to use them as effectively as possible. And so on the technology development side, it's working with individual offices to identify some of the commonalities there. And when you look at the research needs in thermal storage, for example, whether it's understanding increasing power density or increasing energy density, understanding the implications of cycling different ways, looking at how you operate under different conditions. These are all looking at some of the supply chain issues. These are issues that are common to almost all types of energy storage. Obviously, the solutions are different with different technologies, but understanding where those synergies lie and then creating frameworks that allow us to evaluate different technologies that are providing the same services. That's a big part of the technology development work we do here. And then also catalyzing some of the demonstrations that then are going to be more integrated, where we're not just looking at demonstrating one technology and seeing how it performs in isolation, but really understanding what's the intersection and how do you operate, for example, thermal storage in buildings, and what's the value of that when you have certain amounts of, say, battery storage on the grid or pump storage, or you have different types of different types of generation with different flexibility and grid service characteristics. Manufacturing and supply chain is really, again, focused on both reducing vulnerabilities in the supply chain, obviously really essential, and also looking at some of the end of use considerations for different types of storage. Technology transition focused on getting investment, policy and valuation, really, again, looking at what are some of the unique properties of storage that aren't necessarily well considered either in market products or in power system rules or in building regulations, for example. And workforce development is of course ensuring that we have people that are we have both good jobs and people that are trained to fill them. And really thinking broadly, this is an area where another big priority of the administration to ensure that the jobs that we're creating through the transition to the clean energy economy are not just jobs, but real careers that are well paid, offer a level of stability, and are as good, if not better, than jobs currently in the energy sector. So you see here a pretty technology neutral framework and a recognition that storage is both incredibly important and that it's incredibly diverse. And it's, what I'll leave by saying is, part of the reason a structure like this is so valuable is, as you're developing research priorities, we have a lot of experience with many technologies serving a single purpose, or having a given technology serving many different purposes. But with storage, what we really have is many different technologies with many different purposes, and often operating in tandem with other storage technologies or other generation and load technologies. So really understanding where that value is derived from and how the research can then be best optimized to derive the value from a given different technology or application is a big part of what we are trying to do here. So hopefully that's helpful. I'm here to answer any questions and really happy to be a part of that part of the panel. So thank you, Ravi, and thank you, David, for having me.
Thank you, Alejandro. So our next panelist is Professor Luisa Cabeza, and from University of La in Spain. And Professor Cabeza, if you can turn on your video.
Yes, good afternoon. I think it's good morning for you. I cannot share. Somebody should give me the power, please. And now I can do it. Can you see it correctly?
Yes, we can see that. Yeah.
Okay.
Thank you.
Super. Perfect. Okay. So thank you again. Yes, as I was introduced, I'm a professor at the University of Lleida, which is in Lleida, a small city near Barcelona in Spain, where I started to work on thermal energy storage in 1999. But maybe I should also mention that I've been participating in the energy storage program of the International Energy Agency, and I also participate in the IPCC, and today I'm the coordinating lead author for the building chapter. So they're here, there is a lot of knowledge that it's being brought in very recently, because as you may know, we are just finishing the 6th assessment report there. So when I was invited to participate in this panel, which I was very excited to go back into the US, although remotely, the idea was that I give a little bit of the views of my own views, but also what's going on in in Europe on thermal energy storage research in buildings. So one of the slides that I like to bring up usually is this that comes from the International Energy Agency Energy Storage Technology Roadmap. And when they did this easy but nice part of the energy system, already in 2012, it was clear that thermal energy storage has a role both in the supply and in the demand side. And this, at least in Europe, was really important and a breakthrough, because it was a good way to show the policymakers that thermal energy storage really had an important role in the energy system. People knew about ice, people knew a bit about underground thermal energy storage. At that time, people started to know about what was going on in CSP, but it was good that we pointed out that thermal energy storage really had this role in the energy system and today in the energy transition. More recently, IRENA just also did this innovation outlook with thermal energy storage. And again, there, what they highlighted a lot is the flexibility of this technology. And here you see different reasons where they claim this flexibility. And again, giving a big role to buildings. Because you have the demand shift flexibility side, you have the variable supply integration for heating and cooling, you have the sector integration, you may even think about the network management, and of course, seasonal storage. So when I was thinking about also, I was asked to say, you know, where can thermal energy storage could be used in buildings? I think that this is very important because it is just very recently that we are seeing that thermal energy storage can be used in many, many areas of buildings. And again, some of us think on one application or the other. And at the end, I think that really it's everywhere. So I would highlight first decreasing the energy demand of buildings, so going into the sufficiency side. And here, one example is adding phase change materials in the envelope. We see this before. Today, I know there has been work in the US in the past on this, but this is just one example. There are many ways where we can integrate thermal energy storage in our building to decrease the demand, the energy demand, and that is really very important. And here, I think that it will be very, very even more important in the future because everybody is understanding that the better we do our buildings, the less energy consumption there is in the building, then the more important comes the embodied energy, but mostly the embodied carbon. And when we talk about decarbonizing the building stock, we also have to think about this. So therefore, all the energy demand needs to be decreased, and one way is using thermal energy storage in the buildings, either with PCM or with other technologies. Next, we also know that thermal energy storage is very good in increasing the energy efficiency. And I would say increasing the energy efficiency of what? And you can say of anything. I did only add here a few examples. Some of them already also came up today. For example, increasing the energy efficiency of appliances. There are examples today of commercial dishwashers that they use thermal energy storage to increase the energy efficiency. I remember when I first saw this, they were extremely expensive. Today, there is people buying these type of appliances without even knowing that there is energy storage inside, and they are not that much expensive anymore. Of course, you can also increase the energy efficiency of the HVAC systems. Here, there has been a lot of research, and maybe here we could integrate also the ice storage, but using phase change materials in the heating and cooling, but also today, what it's, as we will see later, being very much research is using, for example, storage with sorption systems, going already into the thermochemical energy storage because it has very high energy density. And also, I would like to highlight the idea of also of reusing waste heat. I like when today it was said that buildings also have a lot of waste heat. Some people think that this heat is not useful because it's low temperature, but our temperatures in buildings are low. So having waste heat at 30 degrees is certainly something that could be reused. And here thermal energy storage can also help. We also could go to the next step and use thermal energy storage to increase the use of renewable energies. So when we have decreased very much the energy demand of the building and we have increased a lot the energy efficiency, we may still need more a little bit of energy inside. And then here again, we can implement thermal energy storage to increase the efficiency or the performance of the systems. Again, a few examples here using thermal energy storage in solar thermal systems. It's actually done always. Most of solar systems have water storage. That's thermal energy storage. But there has been a lot of research to improve these water tanks, but we can use other systems also. Today, there is quite a bit of research on trying to do power to heat, for example, with PV, and when there is excess of electricity or there is no demand at that time, transform into a heat to be used later for the building. And I did put here also the idea of the higher use of district heating and cooling. Yeah, calling district heating a bit renewable energy, especially if it's this, let's say, energy carrier is used with renewables. But I also wanted to highlight in this slide the idea of empowering consumers, and thermal energy storage can help a lot on that. All our systems are getting complicated, and then, you know, we have all these concepts of improved control and the data management that came before. But again, here we need to ensure that the users understand a bit these technologies to ensure user acceptability, because this for me is one of the biggest barriers that we have today for this technology. Then if we think about what are the barriers for this technology, some of them also came today. For me, one idea is that if you ask around and you talk about thermal energy storage, most people only know about water storage. If you are lucky, people knows about ice storage. So I think that all technologies are in very high TRL. I have many stories of proposals in Europe that have been not successful because one of the evaluators said there is nothing to research on thermal energy storage. But we know that there are a lot of technologies still at very low TRL, especially those which are more promising from the point of view of energy density. So we do need research on this to make sure that they reach the market. Again, in some applications and some technologies, it can be expensive or more expensive. But in general, thermal energy storage has the reputation of being very expensive. And that's not always true. So there is also, we need to work on showing that it can be a very cost-efficient technology. Up to now, also, the environmental impact has not been considered. Today, with all the concepts with circular economy, this is being known. But even if today you look and you go to the scientific literature and you just put the keywords life cycle analysis and thermal energy storage or phase change materials, there are very, very, very few studies with that. There is much more with LCA and buildings, but not when you consider the thermal energy storage. So environmental impact has not been considered up to now. Again, today, maybe due to this, to get funding, something that has come very fashionable are the biomaterials, and of course, bio-PCMs are included there. But for example, I still have never heard about biosorption materials. No? And for me, one of the biggest barriers of this technology is that it's not well known. And I think that's in all the sectors. So in general, it's not known by society and of course users, but also it's not known by the technicians, engineers, or architects. I still see that at universities, this technology is not taught as per se. If you do a search on how many universities teach that, has like not a subject on this. There are very, very few. Some do talk about thermal energy storage when they talk about renewables in general, but then they barely go into water storage and a little bit more. But today, with energy storage being more important, especially electricity storage, again, there is some universities teaching that, but very little on thermal energy storage. So therefore, also there is a very low knowledge in policymakers. So I was very happy to see that actually you and the US are lucky enough to have DOE really interested now in this technology. Okay, a little bit about the research going on in Europe. It was a bit difficult for me to prepare this, but okay, this is very wide, and if you want more details, maybe I can try. You know, the research in Europe is very, very scattered because we have the European funding, but we have then funding at national level, and then we have funding at regional level. And a lot of this research is either not prioritized or not grouped. So it is very difficult to know even how many projects on thermal energy storage there is in a given country. But it's true that the awareness of thermal energy storage has grown, and there has been more and more research going on this. Some countries more than others, of course. At EU level, already in the 6th framework program, you know that in Europe we work with these framework programs. In the 6th one, which went from 2002 to 2006, we started to see some calls with the words thermal energy storage in there, focus on this topic, and it's when it started to really push research towards this technology. Then next one, FP7, it grew up. Last one, Horizon 2020, there was a lot of research on thermal energy storage. You know, that framework was not technology driven. That meant that there were very few calls that would tell you you need to do research on thermal storage. They were more giving a problem and you had to give a solution. So they would say, okay, you have to decarbonize the building, or you have to improve the energy efficiency of this. And then thermal energy storage could be a technology. So again, it's kind of difficult to know how much money was exactly spent on this technology. But there were a few, and there was at least one call which clearly was directed to thermal energy storage per year. Okay, and one call per year means maybe from 4 to 8 projects that just focus on this, and then you could also use it in many others. So there was quite a bit of work on this. And I think that's why there has been quite a development in Europe for this technology in the last years. Okay, and then I was also asked to see if I could say what needs to be researched. And here at the end, maybe the answer is all. I think it's very important that we need to understand that we need to do research at all levels, so materials level, components level, system level, but also social aspects. I think we need better materials with better thermal energy density, but also with better resilience, so that they really are able to manage many thermal cycles to be there during all the life of the building. We need better components that work better with these materials. In some technologies like sorption, this is more important, but still, we could say in any technology. System levels, we need to show that this technology works, and we need to test it in real systems and in real buildings. Here, for example, one of the most recent research coming out in Europe is the use of artificial intelligence for the control of these systems. But then also we need to work in other aspects like user empowering, user acceptance, new business models, to ensure that the technology will reach the market. And again, at all TRLs. So depending on what technology and what level, we need lower TRL or higher TRL. And that thing, I think, was a mistake because in Europe, for quite a few years, there was the idea that the technology was there. So many calls were for high TRLs. And then the projects were not as successful as it could be because the materials, for example, were not ready, or maybe the idea was too new and we wanted to rush too much. So now there is a bit of going back and, okay, let's also not only, but also give the chance to projects with lower TRL to, for example, develop newer materials. Yeah, I think that's all for everybody. Thank you very much. And open to any question.
I think we will have the questions after all the presentations. So I think our next panelist is Dr. Klaus Daniels from Carrier Corporation. Klaus, can you share your slide if you have?
Yes. Give me just a second here.
While Klaus is trying to fire up his slides, it's probably some of you already know, he just was in Oak Ridge till a month ago and leading significantly large projects on lithium-ion battery and transportation. So we'll get some unique perspectives from him.
Okay, can you see my screen now?
Yes.
Excellent. Well, thank you so much for having me here today, and I'm excited to be part of this workshop. Beside me, I also have two colleagues with me here today at the workshop. Ravi Anapragada, he's a colleague of mine in innovation technology. We're a rather new, small group that has just been started at Carrier about a year ago when we spun off of United Technologies. And then also we have Dr. Richard Lord here with us, who has a long history with Carrier and also a lot of knowledge in thermal energy storage. So without further ado, I'm going to charge ahead and try to save us a little bit of time here. Again, as a lot of people know, Carrier has a long history in HVAC, refrigeration, fire, and safety solutions here. We're a company over a century old, but we have a very interesting opportunity right now as we just spun off of a large multi-component business here, and are now focusing on our core business, and we're focusing on new innovation themes here. And I'm the innovation theme leader for sustainability, so we have a lot of opportunity here in front of us. Just one short overview of what the company is here. Last year, roughly about $17.5 billion of net sales. We have over 80 brands and we're 160 countries. So we're looking at these things worldwide. The customer is really in the focus on there. If you look here, we're looking at goods cooled. We're looking at things like homes protected and alarms installed as some of our metrics here. But without further ado, I want to jump right into thermal energy storage. And I want to pick one example here on things we're looking at. The idea here really is, how can I help with the energy business as well as at the same time do something good for my consumer, right? If there's no benefit to the consumer, then I cannot find anybody who would buy that system. If I look at that, optimal cooling and optimized savings, that can actually be combined by thermal energy storage. You should not have to choose between the two. We've seen similar graphs as this one before, where we're looking at what are the benefits of it. We have a large thermal energy storage activity in France, an engineering team sitting in France, and these this content here is from that group. David Nemzo has shown some similar things where you essentially eliminate peak demand by moving things from the peak to other times by having thermal energy storage in your system. So you reduce operating cost, you essentially have opportunities where you can get smart grid ready, you can communicate with the grid activities and things like that. So with that, I'm going to take one of those aspects where we're looking at things where we are able to shift electricity consumption from peak to off-peak hours. We have systems put together where we are able to essentially eliminate large peak cooling systems of about more than 0.5 megawatt of systems. We provide those turnkey, and we make them 100% smart grid compatible these days. A lot of these things then come with adequate equipment control, plant system management, things like that, right? And here I'll show you one example of an installation. This is a hospital installation we have done in Mongon-Boulsin hospital that's in Martinique. Island nations and island applications are particularly interesting to look at because they have less opportunity for other control strategies because the grid typically is smaller. We have heard Alejandro Moreno talk a little bit about remote communities and things like that. That's really such an application. So if we look here, we're looking at reducing electricity cost in a hospital setting. We need to make sure it's absolutely critical that this will always stay on. There's no time for failure here, right? Because literally lives are at risk at that. So our solution here was essentially installing a nominal capacity of a cooling plant with 4.2 megawatts with a volume of thermal energy storage of about 200 cubic meters there. We installed that. We look at opportunities how to reduce things for the customer. And in this case here, our electricity power reduction was 50% during peak hour demand. And our chiller capacity was reduced by 20%. So those translate directly into real savings there while providing the security of the energy security to the system. And there, the opportunity is actually that you can have a return of investment of less than 3 years. So I thought I'd keep it very short here today and just on this one example to save some time for questions, to have some discussions with my fellow panel members here. And with that, I'm going to return it back here to Ravi and to the panel for further discussion on that. Thank you so much.
Thanks, Klaus. Looking forward to the discussion after this. Ram is our next panelist. Ram, if you can share your slides. And again, as I mentioned, Ram has a very unique perspective. He has been a thermal energy technology developer, and now he works directly with utilities. So it'll be great to hear his thoughts.
Thank you, Ravi, and hope you can hear me and see my slides. Let me get it into PowerPoint.
Yes, it is. I can see it now. It's not in the presentation mode yet, but you can see it.
No, I'm moving into presentation mode. Okay. Great. Thank you, Ravi, and thanks, David, and everyone for the introduction. I'm Ram Naranamurthy, and I'm the lead for the buildings program at the Electric Power Research Institute. And our focus is on strategic pathways to building decarbonization. But a lot of our focus is actually with regards to getting stuff in the field, deployments, looking at pilots, looking at demonstrations, and using that to understand what our pathways can be for decarbonizing our building stock. So when we approach building decarbonization, we are looking at it. Sorry, let me turn on my video. I realize my video is not on. So when we approach building decarbonization, we look at it as a integration of energy efficiency, building flexibility, community renewables, and electrification. So we look at it as how all of these come together so that we can decarbonize our building stock to achieve our 2050 goals. And within the whole building decarbonization piece, efficiency is a core part of the decarbonization puzzle. Whether you go down the electrification pathway or you look at low carbon fuels, efficiency is going to be core to it. It's going to reduce your peak loads, but it's also going to have system-wide benefits. And that's really kind of where thermal storage starts coming in. Because when we look at how thermal storage, what the drivers are for thermal storage as we move towards a low carbon future, one aspect, of course, is grid decarbonization and the changing value of carbon. So it's kind of interesting when you start looking at how the grid decarbonization might impact our carbon footprint. This is a graph from California where you do have a lot of solar. So it's about a 44% carbon-free grid. But what the projection is that as you move towards 2030, 2050, where you need non-renewable resources is going to be the times where we don't expect. The highest carbon intensity turns out to be from 12 a.m. to 6 a.m. Typically not the time when you think of as discharging your energy storage. So I think as the grid decarbonizes, that's something that we will have to think about. And so within that decarbonization picture, when you think about how thermal storage might evolve, what it kind of tells us is that we might have to move from a thermal storage where traditional view of thermal storage is from is for the apps. We might have to start looking at things like heating storage a lot more, because that's really where the value is going to be for decarbonization. Another area that is going to be driving us, especially as more building electrification, is that the impact on the distribution network. When we see all the graphs around how our peaks are, how our valleys are, we've always traditionally fixated on the bulk grid, which is the generation system and where our generation peaks are, etc. But as we go towards the future, and I'll go touch on this a little bit. I know we are short on time. Touch on this a little bit with our deployment experience. We see more and more challenges on the distribution systems, especially the edge of the grid distribution systems, the transformers, the wires. So we see a huge potential for thermal storage at the edge of the grid, which is in the building side, but focus more on how do you flatten the loads, both at the building and on the edge of the grid, the transformers and the wiring. So one graph here kind of shows that what happens when you actually build in really good building envelopes along with some thermal storage potential into the building stock. It shows that you can actually put 30% more homes on a transformer when you build the buildings efficiently. One thing to remember is that the distribution grid is set up as a 50-year asset. So you really want storage that is there for 50 years. You cannot design a grid looking out 50 years if your storage system can be changed in its operating characteristics over the air. So we really have to think about that whole distribution planning at the grid planning perspective and how thermal storage can enable that. Another one, value of thermal storage. As I was mentioning just a little while ago, right? We are seeing more and more winter peaks. Is a great example. Traditionally, everybody thinks of the Southeast as a summer peaking area, but the winter.
Ram, we cannot hear you for some reason. At least I cannot. Can everybody hear Ram?
Ram's audio. Unfortunately, his internet went out right before he had to present. So I know he's having technical issues. But Ram, if you can hear us,
turn off his video.
Yeah, your audio is no longer. We can't hear you.
Okay, hear me now?
Yes, I could hear you. Yes.
Let me try to get through it. Sorry, my again, it seems to be a theme today with the technical difficulties. With my Comcast just went. Let me get back onto presentation mode. So part of what I think I just want to emphasize is that there's two things here. One is let's look at also bring to the fore is the capability of the building envelope to provide thermal storage. When we ran large-scale evaluations with smart thermostats, for example, we saw that at scale with some amount of pre-cooling and preheating, 2 degrees pre-cooling, 2 degrees offset the peak 6 kilowatt hours per home with a $100 thermostat. So when you compare that to an actual battery system, we are doing a lot of with batteries also. Your
turn off your video, maybe.
Ram, your audio went out again. If you can hear us, we can't hear you. And so
can hear you.
If it helps,
Okay.
go ahead and turn off your camera. If it helps your bandwidth, you might want to turn off your camera.
Okay. Let me stop my video. Okay. Can you hear me okay now?
Yes.
Can you hear me better?
Yes, we can hear you.
Thank you. So that's another area that I think I'll just close out with some emerging technologies that are of interest. David talked about the come down to applying thermal storage in our building stock, and things that we are looking at right now that might be of interest is we're looking at modular heat storage for heat pumps. So as we get more electrification, how do you get better heat storage? We are looking at modular construction technologies that can have embedded PCMs and coatings, so that we can do both new and retrofit building. Seems to be interesting is solar organic Rankine cycles for local generation. Use the solar thermal, get your storage in, and then use these organic Rankine cycle machines, for example, to be able interest. Some of the work we did on retrofits, we were able to get a significant reduction in peak loads. For example, using central for using the to Ravi to moderate the panel.
Thank you very much. Can everybody hear me?
Yes.
We can,
Yes.
Ravi. We
Yes.
can hear you.
I would request all the panelists to turn on their video if you can. Except Ram, in case you are having a bandwidth issue, then it's better to have the video turned off. But other than that, I would like all the panelists to turn on the video. And I want to say, first of all, thank you very much for a very engaging presentation from all of you with a different perspective. And with that, we don't have much time. Unfortunately, we are sort of running a little behind. Let me start, first of all, with I'm going to start with Klaus, actually. And the reason I want to start with Klaus is because, as I mentioned to you, Klaus and I actually have worked together, when he was at Oak Ridge, running a lot of lithium-ion battery programs and research. And so I would say that almost all of us here are thermal energy storage buff, but Klaus comes from a very different point of view. He saw the growth of lithium-ion community, and now he is working in one of the largest thermal energy technology companies. So Klaus, the question I have for you, which will be very educational for this community, that I did give an example of how the lithium-ion revolution took place, overall how the community developed and whatnot. But what are the learnings for the thermal energy storage community from that that we can get from lithium-ion community? That's one. And second, how do we go about doing it? What kind of a structure do you think a research structure will help in accelerating what I call a discovery to deployment agenda for thermal energy storage in particular?
Yeah, Robbie, thank you very much. I think this is an excellent question. You have shown it really nicely in the lithium-ion battery community. There was a very coordinated effort, not only just in the United States, but worldwide, right? The community knew each other. They're working very coordinated fashion. The 2019 Nobel Prize, as you referred to here, it's essentially has been shared by 3 people internationally: two Americans with Stan Whittingham and John Goodenough, and their Japanese colleague with Yoshino. And what happened there is that the opportunity was seen in the 80s for what can happen, but then on that coordinated effort really helped it rise up. Lithium-ion batteries came a long way. Just in the last 10 years or so, the price, due to the research intensity, dropped by an order of magnitude. However, for our application, for what we need to do here in the building sector, for anything that goes beyond 4 hours of energy storage opportunity, it's too expensive, and it will likely stay too expensive because the utilization is not there, and the lifetime is an issue in that regard. So we need to find other solutions here. And in that regard, how do we go after that? As a community, we have to come together and we have to define and communicate our needs and our specifications for the application requirements in a much better and coordinated fashion. In that regard, if we come together as a community and have coordinated research efforts, in these hub-like ideas, things like what you've seen there with JCESO or so, we might have a chance to do so. Cost is ultimately the big goal here. If we drive the cost down and make it valuable for consumers to utilize, then that will really drive the market.
Thank you very much. So you mentioned hub. It looks like hub or consortium or whatever we want to call it, but I want to just peel it a little bit further. Do you have something in mind where industry, academia, national labs, policy makers, government agencies, they work together under one umbrella of some kind of structure? Is that what you have in mind?
Yeah, I think that is. I mean, we have excellent contributors around the country here in the U.S. as well as internationally who can contribute well. I think the guidance from industry to make sure that you're providing a valuable solution and that you have a commercialization pathway is really critical. The research entities that participate in it, they need to get adequate funding, but also need to get that focus. You cited USABC as one of the key influencers. They are formed by Ford, GM, and Chrysler in '91. That have influenced how the lithium-ion development happened in the mobile applications, in the automotive applications in that regard. Maybe something similar to that we would need here, where industry essentially can set specifications, where industry can help with where are the critical applications and what are the requirements for those applications. Industry can also help with identifying the really good ideas and the hot topics, and then ensure that the research entities, the national laboratories, academia, those kind of entities, that they are sufficiently funded with the proper focus on them. I think that would really be a key thing. So I would say everybody has sort of their role in this consortium type idea or endeavor, if you will.
Thank you, Klaus. I'm going to go to Alejandro next. You have a very unique role, Alejandro, that you get a very large panoramic view of my own video is off. Okay, let me just switch it on if I can. Maybe it's not working. So anyway, so you have a very panoramic view of the whole energy storage field. So I would like to hear from you, and I think this audience would, that what do you think is the role of demand side and distributed storage in a renewable energy grid, and how important is it for this thermal energy storage community to work at the discovery to deployment time scales?
Thanks, Ravi. It's a really good question, and I think I'll answer the second question first because that's the easier one. I think it's really, I mean, it's critically important. We need all the tools at our disposal, and we know that thermal storage will play a large role. And we know the demand side flexibility, as David was talking about, will play a large role. I think understanding exactly what that role will be is a big part of the challenge in front of us as we learn to adapt to a greater amount of variability from generation and a greater amount of unpredictability from the electrification of large loads that traditionally have been fuel-based. And so, you know, the one thing we can say with certainty is that flexibility of all types is going to be more and more valuable. The specific sort of applications of that flexibility and the technology attributes that implies are going to differ by power system, right? And looking at in the Pacific Northwest, where you have 75–80% hydro, you're going to have very different needs and value proposition from demand side flexibility than you will in a system that's largely nuclear based or largely wind and solar based. That's no reason not to work on both tracks simultaneously. One being really being able to understand the operational parameters and the value that you get from them of different types of storage and flexibility on the system, and at the same time improving the ability of major generation and load side technologies to provide that flexibility. So with the, I think, good confidence that it will be highly valuable in many places, if not in the same way in all of them. So a little bit of a non-answer, but hopefully that helps a bit.
All right, thank you. Go to Professor Cabeza. I mean, you're a world-renowned researcher in the field of thermal energy storage, and you did examples of kind of work in Europe. I think the question is that, first of all, what in the US we can learn from the European experience? And it seems like, and even you mentioned it, there seems to be resurgence of thermal energy storage research in Europe. What are the key factors? And I'm just going to add one more question to this conversation. And how do industry and research labs work in Europe? And we learn from that here in the US?
Yes. Okay. Let's see. Yeah, one of the good things of the European level funding is that we need to enroll industry, but industry also gets funding, and they really then get into research. So there are many programs where industry are required, but they have to invest also in the funding. In these programs, they didn't. So it was much easier for us to get them involved and interested in this technology, even though for them was still, let's say, low TRL to see a real investment. No, it's different today, but 10 or 15 years ago, that was really the case. And the second thing that we really learn, and I want to also link this with what was said before, is that one of the problems of thermal energy storage is that there is not a unique product that you can sell. And here is where the concept of thermal battery came in. I'm sure you heard about this. And for example, the example that was shown today with this equipment done by Sumam, that's how they sell it. They call it thermal battery because it was difficult to Like in a electric battery, usually you have a product that you sell and you can connect. In thermal energy storage, if you put it in the energy system, in the HVAC system, it can work, but if you put, for example, in the building envelope, it doesn't work. So more and more we are using words like this one, like thermal batteries, so people relate it more to a product and they see more the interest. But it's really important, as you said, that the industry works together. But for me, another challenge that is different from the other ones is the building sector itself. In the building sector, there are a lot of times that the final user is not the one who is going to build the building. Therefore, and usually the people who is building these buildings, they want to do it at lowest cost to make money when they sell the building. And who is going to enjoy the advantage of having thermal energy storage there? It's the final user. Okay, so you really need to hear the help of regulations to help people understand that we need to decarbonize the building sector. We need to have buildings with less energy consumption, even though if in theory they are a bit more expensive at the beginning. In the long run, it compensates because you are saving money, But the problem is how do you explain this to a businessman that he builds this building to make money in the short term, while who is going to take advantage of this a little bit higher cost is the final user. Of course, you can always say, well, you sell it higher price, but the user, but they compete and things like this. So the market of the buildings is a bit difficult sometimes, especially if we are talking about putting the materials, for example, in the building envelope. And here in Europe, we have seen that the only way to do it is through regulations. Of course, we need to work in being cost competitive, but again, there are regulations that are also needed.
Thank you. Let me go to Ram. You have a very unique perspective, Ram. I feel that you have worked in developing thermal energy storage technology, and now you work in an organization where you work so closely with utilities. So it'll be great for this community to learn from you. What are the lessons that you've learned?
So I can listen a little bit.
Sorry, can you hear me?
Yeah, I can hear you.
I heard a background voice, so okay.
What?
And so okay, somebody muted me. So Ram, I'm not sure whether you heard my question. Basically, you have a very unique perspective. So what are the lessons that you've learned being a technology supplier, now working on the other side with the utilities? And what do you think will it take for this community to convince the utilities that there is a lot of it can provide a lot of grid flexibility, dispatchability was some of those things which is really important for the utilities, and yeah, I would like to hear that, and then I have another follow-on question for you after that.
Okay, can you hear me okay first?
Yes.
No. Okay, great. It's a good question, Ravi. So having been on both sides, right? I think one of the things that so when we look at how thermal storage is deployed today, it's deployed because of rate arbitrage, which ultimately is an expression of the utility's costs of providing the power, right? Now that's going to change. So we need a little bit more flexibility from thermal storage if you look at it just from a customer perspective. Now, when you look at it from the other side, from a grid, as a grid resource, there's two ways you can use thermal storage. One, and this is the way most battery storage is deployed today, is actually as a controllable resource for whenever you need grid support. The second is as an asset that helps you reduce your grid infrastructure, right? And so part of this, when you look at it as a grid resource, what the grid planners are looking for is, will that resource be there when I need it, right? The consistency and the capability to be controlled by the grid planners, I think, is actually quite important. And that's one of the things I think that I've learned over the last decade or so, right? That when we look at these thermal storage systems, let's look at it. If you want it to be a grid resource, you have to look at it from the planner's perspective on how reliable and how often it will be available. You cannot have it available 98% of the time. If they call it 50 times, it has to be available 50 times, right? So how do you actually design those systems so that it's always available for the grid planners? I think that's really where you will start pulling a lot of value out of thermal storage. So Ravi?
Yes, can you hear me?
Yes.
Yeah, so I have one follow-on question. I think this will be the last question because we are really running behind. I think since you have worked on both sides and you have seen the challenges, and it's a complex ecosystem. You have utilities, you have buildings, integrators, and then you have technology developers. Going forward, again, the same question that I asked, what kind of structure is needed to develop a community where everybody comes together and we can really accelerate all the way from discovery to deployment time frame by, say, 5x, because we just don't have much time left to make for decarbonizing the world.
Yeah, that's a good question. I think you really need a whole bunch of stakeholders. I think we have a lot of them today in the community, right? You have, for example, I'm going to give a shout out to ASHRAE TC 6.9, right? Like the thermal storage committee. You have a lot of the practitioners there. You have a lot of the technology people working on thermal storage technologies here. I think what we haven't done is connect the bigger decarbonization picture through the grid and into how the value is delivered to the customer. So we need to probably expand that tent so you have more grid planners in there so they can tell you what the challenges are and what they want out of energy storage, and probably something from the customer's perspective too on what I call the comfort and convenience benefits that can be afforded by thermal storage. So bringing those entities together from the two ends might actually help people working in the thermal storage industry really kind of look at how we should evolve our products going for the future, whether it's a product that gets designed into the building itself, or it's a product that you add onto a building.
Well, thank you very much. I think with that, I'm just going to end this panel. Again, I want to thank all the panelists on behalf of the audience and myself and the organizers for this great panel, and looking forward to the rest of the workshop.
Thank you.
Thank you.
Yeah.
Thank you very much.
Excellent. Thanks for that, Ravi, and thanks again to all of the panelists. I encourage the panelists to go through the chat and Q&A and respond to some of the audience questions directly, since unfortunately we won't be able to take them due to time constraints at this time. For next, we'll have a keynote presentation from Mark McCracken. He's a leader in the field of thermal energy storage for buildings. Mark is the VP of CalMAC, a portfolio of Trane Technologies. CalMAC is one of the largest manufacturers of thermal energy storage equipment in the world, with over 4,500 installations in 60 countries. In his over 44 years in the energy storage field, he has assisted in the design of hundreds of ice storage systems around the world. Welcome, Mark.
Well, thank you very much, Nelson, for that. This conversation I've been listening to for an hour, it's been fascinating, all the different topics that are being touched on. I have strong opinions on lots of them, which I probably won't have time to share, but maybe they'll come up in the question and answer. I was asked to speak on the barriers to thermal energy storage in buildings. As they said, our company has been doing this for 45 years. I put in my first thermal storage system in 1976 when I joined CalMAC, so a long time ago. And we've kind of lived through all of the changes in this field. And when I ask this question, right, a climate advocate or a consumer utility, a federal regulator, whoever hears the term energy storage, what pops into their mind? It's a battery, right? It's an electrical battery these days. And yet, 10 years ago when Al Gore came out with his book, he had a quote from me that it's dramatically less expensive to store cooling than the electron to create it, right? So it's very clear that thermal is way more cost effective than batteries, but it's really not thought of by our regulators. Now, I always put this up to make sure it's etched in people's mind that the stuff on the left is a form of stored energy. So fossil fuels are stored energy. We're trying to replace it with renewables, which is just pure energy. Where's the storage? We all know on this call that it's not on the grid, or it's certainly not in the grid in the US now, or very minimal amounts of it. I also like to kind of touch on drivers. Other people have mentioned electrification and decarbonization. To me, that means heat pumps, right? And first, I like to make sure people realize that heat pump is a misnomer, right? Heat it's relative, right? These are thermal energy pumps, or thermal pumps moving energy from one temperature level to a higher temperature level. And it's critical that lay people or building owners or developers, they start getting this, that these are energy pumps. And so we're going to start using the thermal energy in the building and pumping it up to levels that we can use in both heating and cooling. And heating, as Ram said, is going to be the really big play for thermal storage as I see it moving forward. I wrote an article for ASHRAE Journal that was in the July 2020 issue on capturing the waste thermal energy in a building in the storage tank in the winter and using it for the next day's heating. So you can kind of refer to that. It clearly breaks up to which side of the electric meter you're on. On the grid side, we know the different options. On the building side, it's going to be electrical storage and thermal storage, right? Those are really the only two options. Now, I put a brief list and categorize it of the benefits of thermal energy storage in buildings that we have seen for decades. It's the most affordable. It reduces energy cost. We can do little or no added cost for the energy storage in new buildings. We can downsize, or what we call right size the plant, which can, changing the plant can pay for the storage in new construction. As far as sustainability, we have materials certainly for ice storage and water storage, 100% recyclable, right? Long life, no degradation. So there's endless benefits of the thermal storage technology that we have right now if we can get them applied in buildings more. Study was done looking at the levelized cost of energy storage for lithium ion versus thermal. The thermal is a third the price installed, and this thermal included the capacity, the chiller capacity, in order to create the thermal energy or to move the thermal energy. So the stuff on the left doesn't have the generation for the battery storage, but the stuff on the right hand side, thermal does. So the costs are dramatically less for thermal. So we really don't have to make that case. But it's not thermal versus electric battery, right? It's not thermal battery versus electric battery. It's what they can do in combination, because they bring different things to the building, right? So the electric battery can run electric devices, right? Which the thermal certainly can't. And it can provide, grid services and backup power, et cetera. Thermal brings other things. It moves a major mass, and I know Dave said thermal energy makes up 50% of the energy that is in a building, overall in a year. My guess is that it's higher than that. Buildings, when you use electrical energy in a building, it then becomes waste heat. So now it's thermal that you got to deal with, right? So it's either putting fossil fuels in the past, that was thermal energy for all the heating requirements, and then all the electrical to get the excess energy in the building in the summer out of the building and pumped outside. So what I say in my talks that I think really has to come through loud and clear is you want to meet electric loads with electrical batteries and thermal loads with thermal batteries, whether it be heating or cooling. And that is the way we're going to be able to tackle the massive amount of energy storage we need. So to give, I'm going to get to the barriers and the solutions I see, but I want to start with a little bit of the history. And some, a number of the people in the call or on this workshop know this, but I look at it as, in the 80s up to 96, I call that pre-deregulation. And as Ram said, we were selling on the arbitrage between the cost of energy on and off peak, right? And utilities were incentivizing storage in the late 80s, early 90s, because they were the major beneficiaries. So the utility would have to invest $1,500 or $2,000 to deliver, create and deliver a kilowatt of energy to a building. Or they could, give the customer that they had, which was a guaranteed customer, $300 or $400 per kW to reduce that demand, right? So it was an absolute no-brainer for the utilities to encourage this technology. Well, when deregulation happened, that separated the benefits. The utility didn't know you were going to be our customer anymore. You might be buying from, Montana or somewhere else. And so it really started, thermal storage and buildings started being driven by other things. It was still the arbitrage because there were cost differences. There were not incentives, but things like LEED, which was based on energy cost reduction in buildings, helped start driving it. And then I would say from 2010 to now, it's all going to be about renewables, saving renewables, and electrification and how we get there. And so with thermal being a third or a quarter or a fifth the price of lithium ion, and it will be as we move into the future, it's going to be a big impact. Somebody asked on how much thermal is installed in the U.S. I had these numbers from 2017. So there was a lot more, megawatt hours of storage being installed at that time. So there's a lot of thermal storage out there. So what's the biggest impediment, right? And the answer is it's complicated. And it breaks down to what we have been trying to do. What utilities have been tasked with two things. They've been tasked with, saving energy and they have two issues, saving energy and reducing peak demand, right? And if you ask them what their real problem was, they would say saving, peak demand is their problem, okay? Now, if you apply a technology like variable speed, if the question is, does it lower energy cost? Yes. Does it save energy? Yes. Does it show in the modeling? Yes. You slow something, a motor down, to meet the load, it's saving energy. So it's a very simple answer to the question. When you get to thermal storage, does it save energy costs? Absolutely it does, right? Does it save energy? Well, at the site, it might not, but at the source, clearly it is. And then you get into emissions, right? And so we have to kind of go back to the source because that's really where energy is being used. Now, if you ask the demand questions, right, 90.1, ASHRAE 90.1 has not dealt with demand in buildings at all, other than energy costs. They didn't deal with it. So, does a variable speed drive reduce peak demand? No. Does it provide load flexibility? No. Those are the things that thermal storage does. And so if you look at it and you're building a house, I use this example, you need hammers and saws to build a house, right? And hammers make bad saws and saws make really bad hammers. So VFDs save a lot of kWh and increase peak demand a little. Thermal energy storage reduces peak drag dramatically, right? And it may save energy at the site. It's going to save it at the power plant. So we need them both. But most of the energy efficiency rules, regulations, they're all based on kBTU per square foot, right? So they completely ignore the when of energy, and that's what renewables are bringing the focus to energy storage. So I wrote an article 2003 on the myths of thermal energy storage. There's a lot of myths out there. I dealt with all of them. Reality is it's a proven technology that and energy. So I said it's complicated. Well, there's a number of reasons why selling storage, thermal storage, is complicated. Because first is, who's the customer? And if you look at it, we have the building owner is the most important customer, or the building developer, right? And if you get them convinced that this is a good technology, it's sustainable, it's saving you money, reducing carbon, et cetera, you have a very good path there. And then you work your way to the architect, engineer, contractor, building operators. And as I said on the right, as you go down the list, the impact of the power these people have to make it go forward lessens dramatically. But each one of them has the ability to nix the project if you have not demonstrated and they don't understand the value to them. And that's a very important part. It's the value to them at each one of their levels. So, you know, I kind of broke it down on the building owner and developer. The value proposition has to be clear, compelling, rock solid. It's dollars, it's carbon, it's sustainability, and this is a really positive PR value for you. For the architect, it's sustainability, it's space, it's maybe lead points, you know, something of that nature. When you get to the engineer, well, now you've got to get into the details of modeling, energy use. They have to know the electric rates, you know, hourly carbon now, which is changing as we move into the future. You've got cost, reliability, heating, cooling. There's a perceived risk from the engineer that that they're doing more design, but they're not getting compensated for it, right? And then contractors, you know, it's always about pricing, and then the operator, it's, wait a minute, I've never seen this, it's new, is it going to work? Am I going to get in trouble? You know, are people going to be cool or kept warm? So as the thermal storage industry, and I was, you know, chairman of TC 6.9 that Ron mentioned, ASHRAE back in the 80s. We've been solving and addressing these things. Oh, the one thing I did not mention there is that the universal constant in sales is salespeople will normally take the path of least resistance. And so if I show you what's on the left-hand side there, this doesn't seem like a low resistance path to make sure all these people, you know, understand what the value of storage is to them as we move forward. Now, I said the industry's been working on this. You know, I said we have 4,500 installations around the world, 60 countries. You know, we've cooled everybody on this call or in this workshop, you know, with ice or chilled water. And I changed things to red that the industry has done and can do pretty well now. For instance, the picture on the right shows that, you know, we've now made a thermal storage system for cooling be a chiller, the tanks, and then everything else is on a package. So it literally, you just connect a couple pipes and you give it power and put the water in the tank and you're off and running, right? So you've taken the risk of the design out of the from the engineer. We know the utility rates. We have programs for doing the cost and the reliability. So the stuff in red we've dealt with, but recall what I said above that, you know, number 3 and up, the things that are in black are the issues that those people have more power in making it go forward, and we really aren't addressing how to attack them very well yet. So what do I see as the solutions? Some of the solutions we need a simplified E+ modeling of thermal energy storage system for an electrified building for heating and cooling, right? So we've been selling cool storage or, you know, ice storage for 4 decades now. Heating with these devices. Now, these ice storage tanks they're not storing ice. ice is the low energy state of water, right? And so when you put energy in, you take that tank from ice to water. So now you have the stored energy. So we are going to be able to use that exact same device for heating and cooling, giving the same benefits of to heating as we have done in cooling with peak load reduction and managing load. This E+ has to be able to do real control options. Why I mean that, I say, what I mean by that is, demand limiting a chiller based on what the peak load of the building is, because normally we have what's called partial storage. You have some battery or some thermal battery being used while you're also running some chiller. Well, you can modulate how much chiller you're using and you can limit that demand. But trying to model that is very, very difficult. Or we want to do what's called ice priority or storage priority versus chiller priority or furnace heater priority. These are control options that have to be embedded in there. And then we have to be able to optimize for carbon reduction, energy cost reduction, and energy, right? And it's always been about energy, really, in most of the systems. And now it's a little more complicated, right? So we need this, and it has to be simplified. And what I mean by that is, I know it can be done by the top modelers, but we need to be able to have a salesperson go in and be able to very easily prove your carbon's in great shape if carbon moves this direction, or energy cost or this. And right now it's not. So that's, I would say, one thing. The next thing we need is more meetings like we are having right here now, right? DOE demonstrating that thermal energy storage is important, right? Because we've collected a lot of people here, and I think we're starting to create a critical mass. I was very happy when thermal storage was moved from the Office of Electricity over to ERE because we were lost over there. We are a building component, mainly for buildings. And finally, I would say what I started it with is educational support of utilities, regulators, and the building industry stakeholders. Thermal storage is not well known. It is not well understood. People just think of an electric battery. That's very easy to do. But just taking an electric battery and putting it on a building and having that battery's electrons go to a compressor to instantaneously cool or run a heat pump to heat something is a waste of those stored electrons. They can be used for much more valuable purposes, like running a screen time, which you can't store, or moving water, which you can't store, pumped moving water or moving air. So there are, these are the things I think we need to really focus about. But when we bring up thermal storage to a customer, they need to know that it's being supported. And one of the biggest things with the utilities when they changed from not incentivizing, when a utility is behind a technology or a concept of energy storage, that brings a lot of reassurance to any customer. And it's really not about the check. It's not about if there's an incentive payment. That's more minor. It's that they're buying energy from somebody who believes in this technology, and this technology is going to last. Now, we've got product in over 40 years. This is Manhattan. I tipped it on its side. We have 120 megawatt hours of storage in downtown Manhattan that's been put in the last few years. So we've got a lot of energy storage going in. And, people say space is an issue, but, we're doing it in Manhattan, which space is as tight as it gets. The future of a low carbon future is going to be about thermal energy storage. One of the things that people were talking about is other technologies. I mentioned the first or other PCMs. The first installation I ever did was for Dr. Maria Telkes. Look her up, Telkes. She was the solar queen. You go to Wikipedia. She was the world's expert on phase change materials using eutectic salts, salt hydrate mixtures. And what she imparted to me back then is something that we have to add to this conversation, that this stuff has to be, thermal storage has to be pennies per pound in its finished version, because you're really competing with water, and water is essentially free. You need to get for pennies a pound because the energy density is, you're going to need a lot of pounds. We're going to talk about active and passive systems later in the day and tomorrow. And thank you very much for this time.
Excellent. Thanks a lot for that, Mark. Similar to the last panel, we'll skip a formal Q&A. Instead, Mark would suggest that you can respond to some of the questions directly in the Q&A and chat box. We'll now go into a quick 2-minute break just to allow people to step away briefly, and then we will jump back into the program.
And people or
Thank
folks,
you very
if you,
much.
yep, you're doing this 2-minute break, feel free to get some water, do what you need. Mark, you did create some dialogue in the chat, so we will pull that out for you in case you don't see all of it. Roderick, I saw you on. Next panelist, please, if you can just come back on and we'll get your cameras and your slides ready to go, that would be great so we can help expedite that. But Mark, thank you for creating such dialogue.
Lynn, can you hear me okay?
Thank you very much. I appreciate it.
Thanks, Mark. Yes, Roderick, I can hear you. Your background looks great. Paul, you're gonna get presentation controls first, okay, Paul? And your background looks great, and so do you. So,
can you hear me okay?
Yes, your audio is coming in clear.
Okay.
Paul, I'll introduce you when everyone gets back, and we'll be able to jump in.
And I'll see some kind of a pop-up that says share, or do I use the share that's on the screen right now?
You should see the share that's on the screen right now. You're the only one that should see it.
Okay. Just to be sure you're not asking me to share now. I'm going to wait till after I'm introduced and then I'll share.
For the sake of time, you can go ahead and share now. I can talk over unless your first screen is which I've seen your slides, so I don't think it's a problem. So you can start with your first slide.
Frederick, how is my sound?
It sounds good. I can hear you well.
Yep.
Okay, great. I'm gonna mute myself.
Thanks.
Hi, Roderick. Can you hear me okay?
Yes.
That's great. I'm just checking my sound before obviously I come in. I'll mute myself now and go to stop video.
Sounds great.
All right. So we've just about had 2 minutes. So this next panel will be moderated by Dr. Roderick Jackson. Roderick is Laboratory Program Manager for Buildings Research at the National Renewable Energy Lab. And this solely helps set the strategic agenda for NREL's buildings portfolio while closely working with senior laboratory management. Roderick, the floor is yours.
Okay, thank you, Nelson. It's been a great morning thus far, so I'm super excited. For those who know me, it's kind of hard for me to contain myself and not be loquacious in my kind of just the way I feel about thermal storage. Because I think the time is now. But in order to really jump into the panel, because we have about 6 panelists and we have a really diverse panel, so I want to make sure that we have time to not only give the panelists time to really share just a snippet of kind of their wealth of experience, really kind of whet your appetite, I would say, for kind of what we would talk about. But also want to have enough time to really have some dialogue, because the panelists we have, they range from startup companies to global companies and large global entities. They range from industry to utilities, one of the largest utility company in the U.S. So with no further ado, I like the way that Mark kind of outlined a few things, such as the history we've seen a transition in thermal storage over the last 40 years. And one of the things that we can say, and that Mark outlined, was the value has changed, right? From the last 40 years, we've seen, even particularly the last 10, we're seeing a shift in the need being driven by renewable energy storage. And so one of the things, or some of the things that our panelists will talk about, is how that value drivers, particularly for their particular industry or their particular needs, we'll be able to talk about. And then finally, I like the quote, the analogy that Mark gave. You have on a job site, you have both saws and hammers, and both need both, right? Because on a job site, saws really make terrible hammers, and hammers make terrible saws. So I think we'll be able to really understand the value proposition that both the thermal storage can provide, and then understand some of the market barriers against that. So first, we'll start off with Paul Steffes. Paul is he really brings a lot of experience to this, because he's been doing this. He's been in this field for over 30 years, beginning in 1987. He's a professional engineer and has proven results from over 100,000 deployments. So he's really, if we want to talk about someone who has been there, done that, Paul is the right guy to help us understand that. So Paul, the floor is yours, or the screen is yours, I guess, in this virtual world. So please go ahead and kick us off.
All right. Well, thank you so much. I just want to start just to touch on our company, and that we started in 1973. But there we had 2 employees, and we had a lathe and a welder and an oversized garage. And today we've grown to hundreds of employees and hundreds of thousands of square feet of manufacturing space. And at Steffes, we have a 1-year plan, a 5-year plan, a 10-year plan, and a 200-year plan. We have this vision of hopefully serving our community, our nation, our world for hundreds of years. But when you have a 200-year plan, you can't think about specific products, but you can think in terms of how can you adapt yourself? How can you perpetually reinvent yourself so that you can meet the current needs of the economy, society, legislative, regulatory, environmental, and political needs? And so it's been with that framework that we've been able to reinvent ourselves every 5 years. And everything we make, we certainly recognize we need to continually improve, enhance, and make it better if we're going to survive. So it was in that date you said, 1987, when we recognized the need for thermal energy storage. And there were hundreds of utilities importing products from Europe. And we came out with a line of products that range from the size of a suitcase to a large refrigerator, so that we can store from 15 to 500 kilowatt hours of energy. Just to kind of compare that with a Tesla battery that can do 8 to 10 kWhs, our smallest unit will hold 15 kWhs. Our largest unit, that is like a large refrigerator, will store 500 kilowatt hours. We heat approximately 100,000 homes and buildings. We in all corners of the U.S.
Excuse me, Paul.
Hello?
Excuse me, Paul. Are you sharing your screen? I know you wanted to share your screen, but it's not coming up right now.
Okay, so I will. Let's see here. How do I go back to my presentation? And I'm hitting share content. Okay, there we go. Okay, here we are. Thank you. Do you see it now?
Yes, we do.
Okay. Very good. So, these devices are from 10 to, 500 kWhs. And in the early days, it was very simple. We simply had to consume electricity from 11 at night to 7 in the morning. But I'm going to show you in these few minutes together how we've developed methods to provide predictable and verifiable dispatchable load to these devices to make, in my mind, this perfect flexible demand device. A true win-win-win for consumer, utility, and environment. Here are the devices. And in a nutshell, I'll just give you a few simple things. We dynamically couple consumer usage to the real-time needs of the grid. So that means that we need precise visibility, controllability, and verification that these assets are doing it, and aggregating them in a very interesting way to bring value to all. This is a technology we've been deploying for 34 years. Various forms of this have been deployed in Europe for well over 50 years.
Hey, Paul, in your display settings, can you go to the top of your screen, hit display settings, and switch? We're seeing your presenter mode.
Okay, display or design.
Display settings. If you go, yes.
Okay, so display settings. I've never done this before.
In your presenter mode. When
Go back to the presenter mode.
Yes. We might have to stay here. I don't see display settings.
Well, if you go back to presenter mode.
Yes. Yes, I'm there. You see this?
And at the top of your screen.
Yeah, there's nothing at the top of my screen though there. It's just all display.
Okay, we can work with this.
Okay. Okay, so you can see the.
Yep. Hey, Paul, we're gonna
Yes.
upload the slides for you, and we're gonna advance your slides for you. Okay.
Okay. Okay. Very good.
Okay. So keep on going. We'll get to the
Okay.
right slide.
So certainly we talked about the technology, and I'm going to touch very briefly. Everyone has heard of the duck curve in Hawaii, but here's the duck curve in California. You can see in 2013 there is very little negative electricity or surplus electricity, and then in 2015 there was a great deal more, and it has to do with all the renewables, all the solar coming in, and so you can see this ever-growing need, for consuming electricity when there's excess, electricity, solar, renewable on the grid. So let's go to the next slide. And this is one of many deployments. But when you have a flexible load, you can display it and you can get it controlling it. You can control it to do whatever you want with the grid, with this flexible load. And you can flatline the load, as others have spoken earlier in this presentation or earlier in the day. Here on this particular day, you can see how we actually followed the surplus solar in Honolulu on a specific day, and we basically charged these 500 ETS water heaters to follow the real-time surplus electricity on the grid. Then during the night, what we did, we only consumed electricity when there was surplus, when there was a higher need, someone who's a high water usage home, we would consume a little bit of the night, but we wouldn't give anyone electricity unless they needed it. So we could basically get well over 95% of the energy coming from the surplus solar. So if you go to the next grid, next slide, please. And, I'll talk about the three basic principles. And this is key to the algorithm to get these, any thermal energy storage, device and many other flexible loads in the home to provide this dispatchable up and down regulation for load following, fast regulation, or other economic or environmental gain. But we want, to consume energy to meet the real-time needs of the grid, ensure that every building has comfort and adequate hot water, but it is key to provide this visibility, controllability, and verification. And that is where we can have this, wonderful, wonderful, kind of controllability. Here are where this is the three modes of deployments that we have right now. So let's just say an off-grid villages, and we have a number of villages like Alaska, where we have a remote controller and it just direct 900 megahertz mesh to all of the homes in the village, and we displace a great deal of fuel oil heat, with wind, and so we can follow the real-time output of wind and do amazing things in these villages. The next one is where we integrate a bunch of homes in a subdivision, and then we talk to the cloud and we aggregate them in that fashion. And we have deployments like that. And then we have ones that talk directly from the home over the home internet to the cloud to get them aggregated in a way that brings value. But let's go to the next slide. And certainly, I'm talking very quickly. I'm doing this 5-minute presentation. Certainly, there is this 1 hour, 4 hour, 8 hour kind of piece to really put some real meat on the bones of what we've done over the last decade with all of the different deployments. And we have communication, but they all have their own limitation. Home internet is beautiful, but when the utilities use it, 15% of the homes lose connectivity in the first year. 10% lose connectivity in addition every year thereafter, and it's very expensive to reestablish that connectivity. And so, you know, there are real barriers to that and other types of communication. And having communication for one device, you know, for our technology is expensive. All of the flexible and variable resources have a need for this social kind of communication to be aggregated in a way that brings social value. Yes, we need to take care of every home and make sure that they have all of the satisfaction they need. But we do, you know, we see value in having this VPN or other type of private network to every building in America. And so, you know, and then the other thing is this recognition has been mentioned before, but thermal storage has many equivalencies as battery technology. And when I talk in terms of this grid interactivity, we bring very high levels of battery, you know, value, you know, to the grid. You know, so with that, just go to the next slide, and I'm prepared for questions when the time comes. And sorry for going a few minutes long, but be aware there's a lot more where that came from.
Thank you so much for that, Paul. I think that's a really, as you say, it's really hours, 4 hour, 8 hour worth of information, but you really gave us a really good gist in 5 or 6 minutes. And so one of the things we're going to do, so we're going to go to Saeed Al-Hala. And so just really quick, Saeed is a research professor in chemical engineering at the University of Illinois at Chicago. And he's the founder of Net Energy. So it's a startup company really focused on thermal energy storage. It's got several book chapters, numerous peer-reviewed and conference journal publications. But really the thing that really kind of, you boil it down and really characterizes Saeed is he's a serial entrepreneur. This is a serial entrepreneur in the space of clean energy, particularly thermal storage. So with that, Saeed, we're going to let you go ahead and kick us off and give us an 8 hour worth of information in 5 minutes again. Wow, we're going to really have some rich discussion. So I'm looking forward to this.
Yeah, I'll just keep it 2 hours. Is that okay? Thank you very much for the introduction and for setting this up. This is actually much needed, and we're thrilled to be part of it. This, you know, everybody's talking about, you know, the value of thermal value props and thermal energy storage. At Net Energy, we focus, at this stage at least, on commercial buildings, where we have done several surveys, and we found that this is where the biggest pain, which is energy cost because of demand and high cost, is probably 30 to 70% of the energy bill. Net Energy Solutions is a thermal battery that utilizes what we call the black ice technology. It is a composite of wax and graphite. And the key thing here is that we do two things that are unique. One is the fascia material can be actually fine-tuned to match the compressor temperature, which later you'll see it actually very critical for compact system and also for improving efficiency. And the material itself, because the composite nature actually has thermal conductivity that is probably an order of magnitude more than ice and other technology. And that's, again, critical because of the concept that we use, I show you later, to move the heat in and out very quickly. It's a modular design which can be actually easily fit to the application. The concept we utilize here is similar to the hybrid vehicles, which probably those of you who followed the transportation industry 20 years ago, 25 years ago, the hybrid was actually a key breakthrough that allowed us to use vehicles without, let's say, compromising by improving the efficiency by using both the best of two worlds, which is the electric drivetrain system and the battery that can provide power and energy unlimited. And the key here are two things. First, you get much better efficiency compared to conventional systems, but also, you know, the user, it's a car. It's similar to any other car that you drive. You don't notice anything except that it actually quiet and much more efficient, and it costs you less gasoline when you drive it. Our system takes the same concept. We integrate our batteries in rooftop units, and the end result is here both a 40%, almost more than 40% peak demand shaving, but also in some cases more than 10% of efficiency improvement. This is just a rendering of work that we're doing with NREL, the National Renewable Lab, and some industry partners. I'll elaborate on that later. But the key here is direct integration. There's no added chillers, no added components. It's basically a small battery that can be integrated with optimized control and smart control that can result in peak shaving and actually significant demand reduction in peak hours. We've been doing this work, actually part of a project with NREL and industry partners over the last few years. And this, we built actually a full system, 510 unit, and it was tested at NREL. And this work here that you see is NREL's team has done some simulation on the work that basically showed that a 510 unit, in this case, we did a case study in a big retail box in California, Belt Desert. But we've done simulation for Baltimore and LA, we get similar results. And what you see here that the system can actually reduce the power demand, especially the maximum peak, by 2 kilowatts, which is very significant, about 30% of the peak demand. Also, what we showed here, which we're still working on over the lifetime of the system, you see by reducing the compressor cycling, you can actually reduce the equipment and improve it cycle life. We also asked our NREL team to look at the impact of this system and technology in general and commercial and residential on the long run if we assume the case of large implementation. And what you see here is a simulation using the Scout tool that NREL did. And this is what's key for us, that it's not just the building owner that benefit. And when you implement this in the large case, you can see the billions of dollars that system can save for the utility. And that's key part for us with our partners now that we work with. And also it can save millions of metric tons of CO2 and terawatts of energy savings. So we feel that this is critical, that it's a win-win-win for the building owner, the utility, and the environment. The project that we've been working on the past few years actually is part of a program that NREL funding, that we got our own funding, but we also, NREL has been leading this with the Technology Fund funded by the Department of Energy. We have commercial partners, and recently we partnered with Exelon, which is our utility, on demonstrating the technology in the field pilot unit that shows that this can actually demonstrate those values in field testing over the next couple of years. Thank you very much. I hope I saved you some time here, and we'll be happy to take any questions.
I think that was great. You really, from a serial entrepreneur, talked about some of the opportunities that you were able to take advantage of, and so I look forward to the discussion. And so next we have Riyad Sawata. I think in this case, Lynn, we're going to show his slides for him and advance the slides for Riyad. I think, Riyad, is that okay where we can advance your slides?
You can. I think I should be able to do it as
okay,
well.
Unless you want to as well. It's your choice. And so as you start to share your screen, he is a co-founder, once again, startup co-founder and chief science and technology officer at Phase Change Energy Solutions. So he's really recognized a global expert and thought leader in smart materials, phase change technology, computational science, biotechnology, and nanotechnology. He holds patents in numerous patents and patent application, and has authored more than 175 scientific papers in this space. He has delivered over 200 invited talks, including the one that he is about to provide here. So with no further ado, Riyad.
Good afternoon, and thank you so much for the introduction and for the invitation. Glad to be with you. I guess, as we heard all day long, the importance of thermal energy storage and how we all listen to multiple points of view. The challenge, as we all know, it is just a quick summary that this is not a unique thing to buildings. It's actually a challenge that we know that temperature control is important in building, in transportation, in many aspects of everyday life. And the idea here that the main point is if you have a system, if it's a building or a shipment, if it's too hot or too cold, it's unpredictable, it means loss, it means many things, from human beings occupying office space. It's lack of comfort, lack of productivity. So having an environment, a solution that serves and solves these problems, it's not only good for the consumer or for the environment, it's also good for the world. Next slide, please. So Mother Nature has laid the foundation for us and gave us many inspiration. And by looking around us, we will always find that Mother Nature gives us a system, a sustainable system in equilibrium, absorbing and releasing heat as needed. In the past few years, or many decades actually, we find that human intelligence expanded on this foundation by either replicating what they found in Mother Nature. And recently, with the advancement of quantum computing and artificial intelligence, we are taking this to the next level. Can we make smart materials, smart controls? Can we transform information, data into information, and really solve big problems? One of the aspects we refer to in many different ways by many speakers today is phase change material or smart thermal mass. Next slide, please. So when it comes to smart thermal mass, if you think about phase change material as a smart material, because it responds to external stimuli by responding to heat or temperature, we as a company in Phase Change Energy Solution, we are about 100 people, about 500,000 square feet of production facilities. We have multiple applications in the built environment, telecommunication, cold chain storage, refrigeration, and thermal energy storage. We approach this from the building perspective initially, and we install today in the building envelope, our energy blanket in over 1,500 banks and over 10,000 telecom data centers and the like. But recently we started looking at the problem rather than actually looking at the whole solution. Can we look and make sure that the building or the system be managed based on a demand basis? So if you focus on the thermal energy storage, or if you can go to the next slide, please. We have systems that can be delivered today in modular form that can be rolled on wheels through commercial elevators into buildings that can be from 25 ton-hours to 120 ton-hours. We have multiple installations in many buildings, data centers, chemical plants, textiles, supermarkets, and even in agriculture and in farms. And the idea here is to do peak load shifting and save energy. I don't have to go through all of the aspects of this, but what is unique about what we offer, if you need a system to go from minus 70 degrees C to 175 degrees C, from deep freeze into refrigeration into waste heat recovery, we can deliver the system because our systems are configured to give you to be able to deal with these temperatures. Next slide, please. This is a nice application I decided to show to the group because this is combining solar with thermal energy storage, 24-hour solar. Can we store the energy using photovoltaic during the day, and then at night, if we need it, we can retrieve it and provide cooling or heating to the system? This is an actual setup on a building on a farm where we're providing cooling during the day and maintaining fresh produce, as well as providing heating to the offices and the other buildings. This is truly a very nice system because if you don't need the energy, you could keep it, it will stay totally intact for a day or 5 days or 10 days. We have demonstrated that. Next slide, please. I'm going to take you now into a system where instead of focusing at the building level as a whole, we would like to put a thermal energy storage in this case for a supermarket. Since supermarkets use a lot of energy, 52% of the consumption in supermarket is in refrigeration. If we actually can manage this, because here, if you look in this picture, you have a lot of thermal mass, but it's conventional thermal mass. If you lose power, that temperature of the products will rise very quickly and go out of range. So what we have been able to do is we offer smart shelves that go into refrigerators and freezers and keep the content exactly at the needed temperature. So in the refrigerator, you have a 5 degrees C, and in the freezer, it could be minus 20 or minus 30, and so on. And in the fresh produce, it's a 10 to 15 degrees C. This way, we are managing the building as a whole by having a minus 20 degrees C phase store tank providing cooling to the system, and then you could turn off totally the chiller at certain times, as you will see in the next slide, please, that if you lose power or you turn off the compressor, you are able to maintain the contents of in the refrigerator or the freezer for many hours without power, 6 to 7 hours. And we have demonstrated this in pharmaceutical settings, where in one location we saved our customer over $300,000 of avoidance of failure. The last slide, please, if we move here. I wanted to put these here as application value drivers and market barriers. So we all know what we are looking for: energy saving, energy storage, temperature management and control, CO2 reduction. We all agree on that. When it comes to phase change materials, what prevented phase change materials to make it all the way? Why it's, as Professor Ibiza said earlier, why don't people know what phase change material is? We have salts that are corrosive, have short life, paraffins who are flammable, plant-based materials who are mainly derived from imported feedstocks that come from certain parts of the world, and we are all familiar with logistic challenges today that can present commercial challenges. The other factor which was really prevented commercialization in a big manner, which is the solid to liquid transition. People went to micro encapsulation, molecular gelling. Today we can make solid to solid phase change materials extruded at 100 degrees C or 120 degrees C. You see here a translucent block of minus 20 degrees C coming in from the extruder at a very high temperature. That redefines the whole equation here, because now you don't have to package it, you don't have to encapsulate it. You could make it the product. It's the primary product, not the secondary product, if it's a ceiling tile or a solid block of gel in a thermal energy storage. Saeed alluded into the thermal conductivity issue, which is one of the big challenges in phase change materials that prevented it. People went into adding additives and composites, but that takes away from the active. Today, you could do 3D printing of 4D printed object that can respond very quickly to the external stimuli that you are trying to do. So now we are employing 3D printing to actually take to the next level without having to take phase change material below 95% active. We all alluded to the energy density many different ways. But today we really need to spend time. We need the scientific community, the Department of Energy, to fund efforts that we take products that are not only from virgin oils or raw materials that are expensive, but from byproducts from the food industry and convert that so the price will be less. In addition, with all the computational toolings we have today, we can rearrange carbon hydrogen atom, do energy stacking, and come up with materials that have energy density higher than that of water. And at the lab level today, we can deliver more than 300 joules per gram in many different ways. So in summary, it's really the form factor, the cost, and the energy density that's going to allow us to penetrate in new markets and solve the issue by having a compact thermal energy storage system that can be utilized in aviation, on electric vehicles, in many different forms. Thank you so much for your time.
Thank you for that great presentation. It was very comprehensive and really outlined the values and market barriers. And so I just want to, as we've had the first three, we're going to have three more presenters on the panel. I just really encourage everyone, because it looks like the panelists are providing their presentation in about 5 minutes. So we're going to have time for Q&A. So please, if anyone has questions, please don't hesitate to include those into the Q&A, to the chat window. And so next we have William Eldridge, and so he is the global head of commercial and industrial sales at SunEp, research at SunEp. He is an executive board director with an exceptional ability to combine both a high-level strategy with innovative solutions into practical delivery. So that's really what, that's a really key point there, because it's one thing to have an idea, it's another to turn that idea into a product, but then actually getting it into the hands of the market is important. And so over the last 25 years, he's both established one and delivered more than many programs and products into the field, and both from emerging technologies and really helping to change the overall environment. So we're really excited to have William speak now.
Thank you very much, Roderick. That's a lovely introduction of me. Obviously, I've got to whiz through the first few slides as they get loaded up onto the screen. I can actually share my screen now, which is great. I'll go off and do that. Excellent. And like I say, so the first few slides I'm going to whiz through so I can really sort of concentrate on some of the challenges of actually bringing thermal storage and certainly phase change thermal storage to the market that we were experiencing as a company. So a little bit about Sunamp. We're a sort of world-leading thermal storage company and systems. We produce active thermal storage batteries. We were established in 2005 and had our first product around about 2011, and we've been really started to be fully commercialized from around about 2019. And we've sold now 10,000 batteries over the last couple of years, and we're on a rapid growth curve up across the globe, effectively in the countries that's actually identified. Major growth in the US this year. So I suppose the two key things that we've done as a company is, one is improve the cyclability of some of the phase change materials that we use. So typically we get over 40,000 cycles with around about 5% degradation, and we've been tested by ZAE Bayern, who've indicated that with 10,000 cycles, they saw actually no degradation of performance. And I think we're the only company at the moment to actually achieve a world grade A for our 58 degrees centigrade material. The other challenge that we've overcome is actually high power in and high power out of separately phase change materials. And we've done that through really sort of understanding the thermal dynamics of the heat exchanger and designing patented heat exchangers now to actually get a lot of power in, a lot of power out quickly. We've got a wide range of temperatures. Hopefully I've moved some to degree F for people who work in that temperature, and obviously I kept it degree C as well. So currently we've commercially got from around about -30 to 118 degrees centigrade as commercial products that you can sort of buy off the shelf now. And they cover a whole range of different applications, ranging from sort of frozen food, flash freezing, right the way through to capture of industrial heat, and obviously in between that, things like hot water and heating. We've also got a number of R&D products that are coming through, typically the 17 and the 81, the 285, and upwards into the 580 degrees centigrade temperature ranges, which is great for things like industrial processes and stuff like that. Like many people, we've really sort of focused on how do we actually contain our phase change material, and that's contained in basically a nice white box with a polypropylene cell, and the heat exchanger is actually immersed within that. And the Unique 3 to Unique 12 ranges is for residential products, and the Unique 8 is effectively our commercial product. This year we'll actually be looking to actually increase the size of our modules, and we're looking to actually build shipping container products that will hold somewhere in the region of 1 megawatt to 10 megawatt hours, depending on the size and the material. So we're definitely bringing industrial products now to the market. Yeah. So the reason that we really was focused and formed by the founders were when they looked at the main problems and challenges of actually going to zero carbon, it's actually thermal energy, which represents around about 50% of the final energy demand. It was the critical thing that they thought needed solving, and what our products can actually do is actually integrate the whole range of heat and power generation that you can get from sort of district heating networks, sort of grid, electricity, heat pumps, chillers, even gas CHP boilers, and obviously solar PV, and actually turn it into products that people actually want, which is cooling, heating, and hot water. And you can see down the right hand side that the value propositions that actually does is everything that people have been really talking about, sort of demand shifting, reducing the amount of capex that grids have to do to actually improve the grid to actually meet the electrification, the zero carbon, and also obviously improving the efficiency of either buildings or processes. But the thing I really want to sort of focus on today is the sort of the 6 key areas that we've been having been sort of challenges to us to actually expand our business, and sort of challenges that we see within the thermal storage, and certainly new thermal storage that's required. One is obviously around the split cost reward, and how do we actually sort of reward people who actually put the capex on, as compared as and in addition who people who pay the opex. So there has to be some commercial models around that, how do we actually do that, or markets that allow that pass through of cost. One of the key areas that we're seeing is we're still in an emerging technology, and there's obviously a cost barrier, has been mentioned, against water thermal storage. Obviously that will decrease as we increase our company size. And the other thing is that we're also finding that we're just completely overloaded by the amount of inquiries that we get. So there's the sheer capacity and ability to actually scale and grow at pace to actually meet demand. There's been much more eloquent people talking about the industry knowledge and acceptance earlier speakers. So I don't want to really focus on that, but yes, there's some real industry barriers within the whole of the supply chain and the industry chain around taking up new technologies. As such, one of the key areas that we're also finding problems with is in essence the regulatory barriers, and especially of coming into new markets, and actually having new products which often aren't linked to existing standards or sort of, as such. So I'm giving an example of that. Currently, we've been trying to actually obtain accreditation for some of our products effectively in the US. Part of that is going through obviously the UL process, and there isn't a standard for phase change thermal storage. So we've been sort of shoehorning effectively our product into existing standards, and making that sort of fit. So I think there's a whole issue around how regulatory standards and regulatory bodies and accreditation bodies actually keep up with the pace of new developments and certification. And I think generally, especially within the phase change material world, I think there's a whole learning that we need to teach people, especially the industry, around specification, and I think improving our standards as an industry to actually meet those specifications. So that's a throwaway and a throw out to other industry colleagues who are working in the phase change. So I think I've tried to keep within the 5 minutes, and hopefully I look forward to questions.
Thank you. I think your experience and from setting up and really articulating full catalog of both value and market is significant and very helpful for everyone as we kind of delve into this to really tackle these problems. So next we have Pradeep Vidas. And so Pradeep he brings, like I said, we have a very diverse and well-rounded panel. Pradeep is coming from Southern Company Research and Development Group. He is the Energy End Use R&D Manager there, located in Birmingham, Alabama. His current responsibilities include both developing the R&D strategy, roadmaps, overseeing the end-use energy efficiency, and electrification projects. He's responsible for coordinating and overseeing the Southern Company relationship with organizations such as EPRI, and we heard Ron speak earlier. And so Pradeep has a very wide breadth of experience in this space, and so we really look forward to hearing the perspective that Pradeep brings from his experience. Well, Pradeep, we're not able to hear you.
Pradeep, if you want to test your audio, it looks like you're unmuted on our side, but we can also, if you're having bandwidth issues, we will have the slides up ready to present as long as your audio is coming through.
Can you hear me now?
Yes.
Hey, I'm joining from my phone. I'm having some problem with connectivity.
So we have your screen.
Yeah, we have your slides up and ready for you. If you want to just talk through them, that'll be great. We have it on the title slide for you, so you can start at any time.
Thank you so much. Hey, once again, I'm manager for Energy and Use R&D Group, which is Southern Company. I'm talking in terms of utility perspective of thermal energy storage systems. Can you go to the next slide, please? Third slide. We can come back to the next one. When it comes to application of thermal storage, I split into two groups. One is what is for utility and what is for my customer. For utility, historically, we always went for typically, for managing the summer peak, especially for southern region of Southern Company. But now we are moving from not only summer peak for 8760 flexibility. Why is that important? Because we are seeing more and more renewable energy coming to the market, and also technologies enabling that we can have more flexibility. In addition to that, Southern Company with high penetration of heat pumps in the last 10, 15 years, we are not only summer peak, we are also winter peak company. So we are looking for both summer and peak, winter peak management, as well as for 87 flexibility for either grid resource or grid planning or generation planning, different things. Okay. And while it provides that, I'm increasing the value of our electric products, whether it's a water heater or thermostat or refrigeration. That means I'm increasing the value of water heater, not only for heating the water, but also for thermal storage. So I'm still questioning what I can do in terms of carbon management in the future. Okay? So when it comes to retail customer, definitely number one is what is for them. Okay. They're also installing renewable generation, and they're also looking to see how they can integrate renewable generation with energy storage. Okay? That's number one. Number two is the value in terms of cost. Can they reduce peak demand? Can they integrate with the time of use rate, retail time, RTP rate, real-time pricing? There are many, many rate innovations coming to the picture. At the end of the day, although I may promote as a utility, the customer has to see the value. Okay? Go to the previous slide, please. So we have a number of R&D projects, demonstration projects, all the way from residential applications to commercial and industrial applications. Because of limited time, I'm just showing one project are one set of projects, which I call smart neighborhood projects. In other words, from DOE standpoint, they may call it as connected community projects. So we have two major projects. One is at Alabama Power, which is in Birmingham. It's both are called smart neighborhoods. One on the right, we just completed. It's a 62-home, single-family home. We have a microgrid as a community level, not at the home level. The connected microgrid consists of solar, energy storage, and generator. So here we were managing through the grid, microgrid, community scale, as well as water heater, and as well as thermostat within the home. Okay? And also other neighborhood is that's in Atlanta that just completed construction. We just started collecting the data. It is a 46 townhome facility, unlike Alabama Power, the one on the right, the one on the left, which is in Atlanta. It's a home-based microgrid. What does it mean? We have solar panels as well as energy storage within the home. So here we are trying to manage all the assets within the home, including solar, water heater, HVAC, water heater, as well as EV charger. Okay, so we are testing them, not only technology, right, the real world application of these technologies. I want to point out, based on our experience, customer behavior when it comes to homes is even more important than technologies. How, for example, we try to control both water heater and thermostat. See, water heater, it's an 80-gallon heat pump water heater. They did not see an impact of preheating, so they didn't touch anything. But when it comes to thermostat, anything beyond 2 degrees, they bypassed our settings. More than 80% of the people. So we have to be very careful on not impacting the customer, whenever we are trying to implement these kind of technologies. Okay. So that's why I want to share. Okay, go to the next one, please. So when it comes to barriers, definitely one is when it comes to customer, the smaller to large, the value must be demonstrated. Why? It's still a complex topic for a customer, not easily understood. Especially for home, they don't know what is meant by thermal storage. They don't know what is meant by rates and all those things. And we still feel the costs are high, although it is coming down, but it needs to come down significantly. Number 3 is the important one I want to mention is, we do all this grid interactive, connected, and use devices. But at the other end, distribution people, they're not seeing it. They're not connected. We are telling them the value for them, but they're not connected right now. So we must look for DOE and other entity R&Ds. We must connect it with the grid planning groups. So in order to take the advantage. Otherwise, it'll continue to be a niche market. Okay. In terms of site and like the complexity, connectivity is equally important. We are looking for, depending on the customer, connectivity, connecting with the, whatever the tools you're planning to use, they have to be reliable. And we have not seen that on these projects. It's still working on it. It's improving, but there is still a gap. So I just want to, so in addition to this residential, we also have projects related to working on the campuses and commercial buildings and all those things. So these are the things I thought of bringing to attention. Okay. That's all I have.
Thank you, Pradeep. I think you said this is real world applications, and then you gave us some real world challenges and barriers to pushing this from you, to use your terminologies, to go from a niche to real widespread applications. So thank you for that. Yeah, that was great.
Yeah, I went fast because I had 5-minute time, so that. Yeah.
I know for those that I've worked with Pradeep on some of those first homes that he talked about, so he has a wealth of knowledge. So I was sitting back listening, enjoying. So, and finally, we'll go to Juan. Juan really kind of this is the last panelist here, Juan Catano, and one of the things, he's coming from Emerson, so he's really kind of a great round out this panel. So Dr. Juan Catano, he leads the system analysis work for Emerson's research group focused on comfort and refrigeration systems of the future, and really moving, not in-kind cooling technologies. So he's a tech lead for their collaborative research investment, including with the national labs. So I think one of the things that a really great segue from Pradeep talked about the two neighborhood projects that they did in concert with the national lab, and one of the work that Juan does as well is really helping to kind of foster these collaborative research environments. We heard in the previous panel about how these types of hub consortium kind of really helps to move the market forward. And so I think this is great that Juan also brings these types of activities and experience to bear to really talk about how do we move thermal energy storage forward. So no further ado, I love the picture. So I don't know if I like the picture more or just so we'll see what we'll let Juan go ahead. So thank you.
So, hello everyone, thanks for joining us today, and I'm very excited to be part of this panel because I'm a strong believer in the potential of thermal energy storage to reduce the environmental impact of buildings. And even though sometimes moving the technology forward feels like we're climbing a mountain, a nice mountain, I think we might be getting closer to the top. So that's why I picked this picture. So as many panelists before me have discussed, there are several advantages of using thermal storage. So they mentioned that thermal loads are the main contributors of the energy consumption in buildings, and storing thermal energy storage is cheaper than electric batteries. But one key thing is that they're not one versus the other. I think they're complementary. So I think that's one very key point to take. Mark mentioned that earlier. But I want to focus on the fact that not all power is created equal. The time you consume energy is as important or even more important than how much electricity you're using. So if you take a look at this plot from whattime.org, you can see that from a CO2 emission standpoint, there are clearly optimal times where you could be using energy, and there are certain times that you want to avoid. But one thing that I want to point out is that this plot is going to be very dependent on where you're located, and it's going to vary day by day. So the flexibility that thermal storage brings to the building is a key thing to achieve the lower carbon intensity or lower carbon emissions from the grid side. So if we look at the value drivers, I think the flexibility is the key thing that we want to discuss. And flexibility comes in two big levels. One is the design flexibility. We can design a system to match your local needs. So we can size the compressor, size the heat exchangers, size the battery size for a specific building needs. And the other thing is that we can design the controllers also based on those needs. So we have the weather, we have the utility rates, we have the technology that is available for the building, and you have the building loads. And based on those, you can design your system and also control your system. So when you're controlling the system, you can decide when to charge, when to discharge, or if you want to go to hybrid operation, and that's charging and discharging at the same time. So this type of technology brings a lot of flexibility to your designer, to your operation of your system. The second value driver that I want to mention is that it requires no behavioral changes, and there are no compromises needed from the user. So you can get the same level of comfort or even more comfort than the traditional systems, and you don't have to do any changes to how you operate your system. So you have a similar user interface, and the difficult decisions are done behind your meter. So you can have cloud-based optimization, and you can do day ahead optimization at the cloud level. So the user doesn't have to know what's going on behind the scenes. So the user is going to get the same or better performance with this type of technology. So there's no need for behavioral changes, and I think that's a key thing to get from this type of technology. And the third value driver that I want to mention is that there's a benefit to multiple stakeholders, and this has been discussed in previous presentations. But I want to mention that there's like benefits all across the value chain. So you have benefits to the building owner or building user as like reduce energy cost, but you also have benefits to the generation station. You have benefits to the transmission distribution lines, and you have reduced carbon emissions, and you have improved resiliencies. So you have benefits across multiple stakeholders. And even though I am including this as a value driver, this could also be a challenge or a barrier. So this brings me to my next section. Of market barriers. So since there are multiple stakeholders, I think it's difficult to make the value propositions just from one stakeholder point of view. So you need to bring multiple stakeholders into the picture. So you need to see what is the benefit to the utility, what is the benefit to the building owner, what is the benefit to the government by reducing the carbon emissions. So there are multiple people or stakeholders that are going to have advantage by implementing this technology. So how can we bring everybody together to take a benefit of implementing this technology in the field? The second market barrier, I think, are the electric rates. Electric rates are not designed to capture the full benefit of thermal energy storage. And the other thing is that the electric rates vary widely across the United States, and sometimes they're not transparent. So sometimes it's like you have multiple options and you don't know what is going to be the best option to choose if you're transitioning into a thermal storage solution. And third is give me 1 second. The system metrics. Current system metrics for HVAC cannot capture the full benefit of adding storage. So if you look at traditional vapor compression cycles or the traditional HVAC systems, you have very static metrics. So you focus on efficiency at a static point. You look at ER, SEER, HSPF. So those metrics cannot capture the full benefits of adding storage to the cooling solution to your building. So I think we need to work on adding improved metrics to capture the full benefits of thermal storage. And as we have mentioned before, there's also the customer perception. Customers usually assume that these type of solutions are lower efficiency, are too expensive, or high complexity. But I think these metrics are wrong, and you can have system solutions that are higher efficiency, are close to the baseline cost of the system, and the complexity is managed behind the user interface. So you don't need to deal with the complexity, and the complexity is nothing that the user needs to be worried about. And also one key market barrier, I think, is the seasonal operation. I think we have been too focused on using thermal storage either for the summer or for winter application. But I think we need to start looking at application or system configurations that can take this thermal energy storage into an annual operation. So you have a system that can reduce your energy loads in the summer, but also in the winter months. So seasonal operation is going to be key to making the value proposition much easier for any particular stakeholder. Also, I want to mention for those of you that might not be familiar with Emerson, that we are a global company with two main businesses. We have an automation solutions platform and a commercial and residential solution platform. And between the two business units, we have products across the value chain from energy generation, distribution, and from the thermostat that is implemented in your home. And with that, I'm looking forward for the discussion.
Wow. So I really love the fact that your presentation ended really kind of summarizing some of the challenges and market barriers that Pradeep outlined, saying that until we bring together both sides of the coin, both the generation and the building side, that's one of the barriers. And so that's one of the things that you're saying Emerson is doing. I've been getting messages from the organizers saying that we are limited on time and that I don't have time for discussion. However, I will, unless I can ask for more time. But I think in order to really make sure that we use the breakout sessions, they want to kind of move to that. However, I will say this: the last hour, I have been looking at thermal storage for particularly kind of in buildings for at least the last 5 or 6 years. And I haven't seen like this type of diverse perspectives on really articulating the value as well as the market. So I want to thank the panelists for really outlining that, because what it did was it really showed that we have some perspectives, some market barriers that are similar that we kind of all describe, but we describe them in different ways and really kind of capture the challenge. And so with that, I do want to add, I guess I'll take presenter panel moderators. I'll take that privilege and just ask one question for everyone to consider this afternoon, an additional barrier maybe that we didn't talk about. One of the things that David mentioned in his earlier slides, we want to make sure that the benefits of thermal storage, the benefits of the clean energy transition are shared by all communities. And so one of the questions I want to ask that particularly Pradeep mentioned, he asked about, well, we have to understand the customer. The customer has a very big impact on the outcome. And so the question is, as we think about all communities, particularly communities that we have prioritized in the past or communities that we haven't prioritized in the past, thinking about some of the initiatives coming out of the current administration, how does thermal storage, how do we think about the barriers? How do we think about the differences between communities? How does that impact the market barriers? How does that impact the value proposition? How does that impact how we communicate those value proposition and market barriers, as well as the technology solutions and other solutions that we deliver? So I know we don't have time. I wish we had time to really talk about that as well as other items, but I am getting the hook from the host, and so I just wanted to really add that to the conversation. Let's also think about beyond in addition to the market and value we articulate, let's think about how the people and the different people and how we want to ensure that the solutions we deliver are readily applied and benefits derived by all. So Nelson, I think, kind of got us a little bit back on schedule, not too far off, but just really thank the panel for their awesome presentations.
Thank you, Roderick.
Yes, thank you again to the panel. And if the panelists wish, there's some questions in the chat that they could answer directly as well. So we'll now move into the breakout session portion of our program. If we go to the next slide, so you all have been slotted into various breakout sessions based on your preferences. We will be set there automatically when the session host decides to split us. Just a little bit of guidelines for the actual breakout sessions. So we will allow people to talk in these breakout sessions. However, they'll still be fairly large. So to help maintain a bit of order, please try to raise your hand. And then each session will have a facilitator that can call on you to speak and help guide the discussion. Make sure your microphone is muted when you're not speaking. When you do speak, you can introduce yourself, name and organization. And we also encourage you to make ample use of the chat functionality while in these breakout sessions. So just due to the numbers, it's unlikely that everyone will get a chance to speak. However, to ensure that DOE is able to receive your feedback and help guide future directions, please try to use written responses to allow us to record that. And with that, Lynn and Lindsay, I think we are ready to go to the breakout session.